Please give me a thumbs up if everything is fine. Okay, wonderful. Right. So let's begin with our session. So yesterday we had begun with the chapter on space technology, and in space technology, our discussions had begun on celestial bodies. Now, in celestial bodies, we'll continue from where we left, and the next discussion that we have is on planets. So we discussed about stars, we discussed about the sun, we discussed about some of the important phenomena on the sun, and all these other discussions that we did. And from there on, we continue, and the next topic for us is planets. Now, from the perspective of planets, first and foremost, what we need to understand is that how exactly do we define something as a planet? You might know that, for example, all these are called as planets. Now, for something to be defined as a planet, just understand this, that something to be defined as a planet, there are a total of 3 criteria. And if these 3 criteria are met, then in that case, you'll say that these are planets. Now, what are these 3 criteria? The first criteria is that it should orbit the sun. So any astronomical body that is orbiting around the sun, we can say that it is a planet. Second point is that it should have sufficient mass for spherical shape. So what we discussed, that just something that we discussed for the stars as well, that they would have a gravitational stability, and this gravitational stability will lead to a spherical shape. so this is due to gravitational force. So this is due to gravitational force. So with the help of gravitational force, they will have sufficient mass for having a spherical shape. Now, the third point, what happens is, and what you'll see if you go back to the history of defining the planet, you'll see that these two first criteria that we have here, these were the only 2 criteria initially to be defined for something to be defined as a planet. That they should be revolving around a star, and secondly, they should be spherical in shape, or let's say almost spherical in shape due to their gravity. This was the time when Pluto also used to be a planet, right? But after that, what we saw was that Pluto was taken away from the list of being a planet, and this happened when there was this third criteria added, that it should have cleared its orbit. Now, when we say that it should have cleared its orbit, what is the meaning of clearing the orbit? Understand this, that when we say that it should have cleared its orbit, what is the meaning of clearing the orbit? So when we say that it should have cleared its orbit, it means that it should have a gravitational force in a manner that anything that is in the surrounding area should not exist, meaning that they should have either collapsed on this planet itself, or maybe they would not have been bound by this planet, and they would have just flown away somewhere. Now, in case of Pluto, this was not the case. In case of Pluto, this was not the case. What happened is, and this is how the things went, there is another planet which is near Pluto called as Aries. There's a planet called as Aries. Now, this Aries, when initially they were observing Aries, they found that Aries was bigger in size than Pluto. All right, bigger in size than Pluto, spherical in shape, orbits the sun. There is no reason why we should not classify Aries also as a planet. And this is where the discussions began, that Aries should also be called as a planet. Now, what they thought, what the scientists thought, is that the list of planets in the solar system should be an exclusive list. It should be an elite list, and we should not keep on adding every planet that we see or every new celestial body that we discover. So this is where they thought that let's add another criteria, because this Aries was very near Pluto. All right, it is in close vicinity to Pluto, and yet Aries has its own independent orbit around the sun. Normally, what happens that if there is any celestial body near a planet, they would revolve around the planet. They would become the satellite of the planet, right? Or they might have collapsed to the planet itself while the formation of the solar system was happening. But this was not the case with Aries and Pluto. Here, Aries, bigger in size than Pluto, spherical in shape, orbits the sun. Only one thing, that Aries was seen to be very near Pluto. It was in the close vicinity of Pluto. So this is where they added the third criteria, saying that the third criteria would be that it should have cleared its orbit, that it should have good enough velocity, it should have good enough velocity, good enough gravity, let's say, to not let any celestial body have an independent existence. Right? So if there is anything independent existence near this planet, all right, so anything that is near this planet, it should not have its independent existence. So this was not the case with Pluto, because Aries was found near Pluto, bigger than Pluto, orbiting the sun. So that's why it should have been also classified as a planet. But then they said that, okay, fine, these two are near one another, so neither will classify Aries as a planet, nor Pluto would remain a planet anymore. And this is when, and this was 2006. This was 2006, and this is when Pluto went out of the list of planets. This is where we ultimately saw that Pluto was removed from the list of planets, and this is where we understood that now this third criteria became important, and from 9 planets we were reduced to 8 planets. Fun fact is, later it was found that Aries is actually smaller than Pluto. So if it was the initial observation, then perhaps Pluto might not have lost its planethood. Then Pluto perhaps would have remained a planet even today. So that's why the story of Pluto is a bit unfortunate, that it was not Pluto's fault, but our fault, that we did not do right observations initially, and yet Pluto lost its planethood. There are still warriors fighting for justice for Pluto. If you go to Instagram and search for hashtag, there are hashtags saying justice for Pluto. That there people are still looking for justice for Pluto. There are warriors like me who are still fighting. The scientists also once in a while discuss that should we again bring back Pluto in the list of the fold of planet, because it was not Pluto's fault but ours. But we can't say anything. So ultimately, this is what happened, and Pluto ceased to remain a planet. All right, so this is how we define something as a planet. Now, in this case, when it comes to something like Pluto, all right, when it comes to something like Pluto or Aries, etc., whenever the third criteria is not fulfilled, we call them as dwarf planet. Right? They are called as dwarf planet. So when the first 2 criteria are fulfilled and the third criteria is not fulfilled, then in that case it is called as a dwarf planet. So that's why Pluto is now called as a dwarf planet. Aries is called as a dwarf planet. We have Ceres, which is the only dwarf planet in the asteroid belt, right, between Mars and Jupiter. All the other dwarf planets, they are beyond Neptune. Only Ceres is one dwarf planet which is in the asteroid belt. So these are all now dwarf planets. Similarly, the other planets which are outside the solar system, right, which might be revolving around any other random star, they are called as exoplanets. So we have another kind of planet called as exoplanets. So exoplanet, these are the planets outside the solar system. Right? These are planets which are outside the solar system. So they are called as exoplanets. So in this manner, what happens is that exoplanets basically are the ones which fulfill the criteria, just that they are outside the solar system. So this is basically what is happening. So that's why more than the first and the second point, the third point is important. That third point simply saying that in the orbit of this planet, there should not be any other celestial body which is near this planet. And if there is something near this planet, it should be revolving around this planet just like a moon, just like a satellite. So it should not have an independent existence near this celestial body or near this planet. So that is what it means by clearing the neighborhood or clearing the orbit. So this is how we basically talk about planets. All right. So this is how we define planets. Now, when it comes to planets, there are certain things that we should always know. There are certain things which are unique about a given planet, and the things which are unique about the planet are the ones, if at all a question has to come from here, these are the areas from where questions would be asked. So, for example, let's say when we talk about planets, it used to be a very common topic. It used to be a very favorite topic of UPSC, but we have seen that last 10-12 years they hardly have asked any question. What I believe is the questions on celestial bodies, what we have seen is that for a very long time they were not asking questions. Last couple of years, I have seen that again they have started showing some interest in celestial bodies. They have started asking some questions on celestial bodies. So this is what I think, that now going forward, perhaps they all again remember they're one of those favorite topics, and they might come back and they can ask questions based on it. Now, when it comes to these planets, and if at all they have to ask questions based on the planets, then there are certain things where the questions can be asked from, and these are things which are unique about the planet. Anything that is unique about the planet, if at all they have to ask a question, they will ask a question from anything that is unique. All right. So for example, for each and every planet, there is something that is unique. And I'll keep asking you, and I'm sure many of you know the answer. Wherever you don't know, anyway, I'll keep on writing all these things as well. So I'll ask you certain questions, all right? And you please give me the answer. My first question is, which is the hottest planet of the solar system? Which is the hottest planet of the solar system? Quickly. Yes, as many of you have mentioned, it is Venus, and it is not Mercury. Right? So this is very, very important for us to remember that the hottest planet is Venus and it is not Mercury. Although Mercury is the closest planet to the sun, but still Mercury is not the hottest planet. The second planet to the sun, which is Venus, Venus is the hottest planet. Anyone, if you can tell me what is the reason why is Venus the hottest planet of the solar system? Yes, atmosphere. What exactly in the atmosphere? Carbon dioxide. Correct. So what happens in Venus is that Venus has a thick atmosphere which is composed of almost 95.5% carbon dioxide. 95.5%. And that's why it traps a lot of heat, because carbon dioxide, we all know, is a greenhouse gas. Why do we call it as a greenhouse gas? Because it can trap heat. Correct. Same goes for the Earth, that when we are talking about global warming and climate change, we know that greenhouse gases are the most problematic culprits here. Correct. Greenhouse gases only lead to climate change, they lead to global warming. Now, on the Earth, how much of carbon dioxide do we have? It's almost 0.04%. So only with 0.04% of carbon dioxide, we are carrying global warming. So just imagine when you have 95.5% carbon dioxide in the atmosphere, what kind of heat they have been trapping. So that's why Venus is the hottest planet of the solar system, because of the heat trapping capacity, heat retention capacity that it has. Because of that, we see that this is something that happens here. So Venus is the hottest planet because the atmosphere is made of carbon dioxide, 95.5% carbon dioxide. All right. So that's why it is the hottest planet of the solar system. All right. So that is one important thing. Then after that, one more point, and this is also about Venus, that Venus rotates from east to west. So it is the only planet of the solar system, not the only planet actually. Venus has a direction of rotation from east to west. All the other planets, they actually rotate from west to east, and Venus is a planet that rotates from east to west. Why rotates from east to west? It is said that, and this is a popular theory, I'm not saying that this is the exact explanation, this is a popular theory, that when the formation of the solar system was happening, at this point of time, Venus might have collided with some other celestial body, something else, which was near Venus, and because of this collision, its rotation direction would have changed. So this is what we say about Venus, because of which we believe that it might have lost, it might have started rotating in a different direction, in an opposite direction. All right. So these are things that we know about Venus. Venus is believed to be a tropical planet once. It might have been a tropical planet once. It was the first destination. All right. What you see is that if you go back in history, like 40, 50 years ago, and you'll see that all the expeditions and all the plans, all the missions that the world was planning, whether NASA or European Space Agency, they were all planning it for Venus initially. Because Venus, you might know, is the closest planet to the Earth. It also is sometimes called as the sister planet or the twin planet, and it's called so because it is in size also it is very close, and it lies in an area where it is believed that it is very close to having a possibility of sustaining life. So that's why the first destination that we were interested in was not Mars. It was Venus. We started with Venus. But as soon as the first mission was sent to Venus, we understood that we can't come back to Venus, because first of all, the heat trapping, because of which we understood that the temperatures are very, very high and it's very difficult to survive there. At the same time, what we also see is that Venus constantly sees an acid rain. An acid rain happens because of the presence of hydrogen sulfide. So sulfuric acid is made in the atmosphere, and it rains sulfuric acid on Venus. So that also creates a condition which is not livable. So what happened is that the probe, the mission that was sent, we very soon, as soon as it was sent there, as soon as it entered Venus, very soon we lost contact with it, and then we realized that Venus is not the destination. So that's why we saw that ultimately we stopped going to Venus and we started looking towards Mars. Then, all right, so this is what we know about this. Then, if we talk about Mars, Mars is called as the red planet. Can you tell me why it is called as the red planet? Why do we call Mars as the red planet? Yes, presence of iron, perfectly correct. So, called as the red planet mainly because of iron, correct? This is because of presence of iron oxides. So iron oxides take a reddish color. For example, even if you consider rust, when corrosion of iron happens, so you'll see that also has a reddish brownish color. So because an oxide of iron is formed there, so wherever you have iron oxide, this is something that will happen. This is how the things will shape up. Then, can you tell me which is the densest planet of the solar system? Which is the densest planet of the solar system? This is an interesting question where I need to understand the answer. Okay, Shubhajit, you are correct. Hitesh, you are correct. Amrit, Prince, Vikas, correct. Shovik, correct. Devo, correct. Abhijit, Tushar, correct. Anshu, correct. Ilma, correct. Arun, correct. Wonderful. So many of you have given the correct answer, but many of you have been giving wrong answers. Many of you have said Jupiter, and Jupiter is not the answer. The densest planet of the Earth, densest planet of the solar system is the Earth. So don't forget that we also are living on a giant planet. Not to forget that our own planet is the densest planet. Now understand why we are saying that these are densest planet, and first and foremost, why Jupiter cannot be an answer. Why Jupiter or Saturn, etc., that some of you have written, they cannot be answered. Why? The planets, when you count the planets like Earth or Venus or Mercury or Mars, these are planets which have a solid surface. All right, they have a solid surface. Whereas when you look at the other planets, which are outer planets, Jupiter, Saturn, Uranus, Neptune, these are planets where they are called as gas giants. They're called as gas giants because they're very large in size, but they are gaseous. All right, these are gaseous planets. They do not have a solid surface. So when there is no solid surface, it means that mass will be low. Correct. Mass will be low. So what is density? What is the formula for density? Mass divided by volume. So mass will be very low for these all planets, although they are huge, they are big. But mass by volume ratio will always be very low because they are gaseous, they are not solid. So that's why a planet like that can never be the answer. So Earth is actually the densest planet of the solar system, and this is where remember the difference between inner versus outer planets. So we have planets which are called as inner planets, and then we have outer planets. So how do we define what is inner and what is outer? So inner planets, first of all, inner planets, they are found between the sun and the asteroid belt, and they are found beyond asteroid belt. They are found beyond asteroid belt. Then they have a solid surface, and these are called as gas giants because of gaseous surface. These are gaseous planets. Okay. Now I have a question for you. Okay. I have a question for you, and please answer this. I'll launch the poll also for you. Which of the following planets have rings? Okay. Jupiter, Saturn, Uranus, and Neptune. All right. I'm giving you the options: 1 and 2 only, 2 only, 2, 3, and 4, and all of the above. Launching the poll. Quickly mark your answers. So 21% of you have marked A, 32% B, 17% C, and 30% D. 30% of you are perfectly correct. The answer is B. Just remember that all the outer planets, they have rings. All the inner planets, they don't have rings. All the outer planets, they have rings. So although we know about the rings of Saturn, the rings of Saturn are the thickest of them all, and that's why rings of Saturn are very well known. Whereas all the others, this is where we see that their rings are very thin. So that's why they are not known for their rings. But all of these 4 planets, they have a ring system around them. It was discovered late, but we saw that they all have rings. So that's why all of you who marked D, that's the correct answer. All right. So that's also something which is unique about all these planets. Then apart from all these things, there are some of the other facts also which can become important. For example, we talked about the hottest planet, that the hottest planet is Venus. Then if we talk about which planet that records the lowest temperature. Can you name the planet that records the lowest temperature? Yeah, so everyone is writing Neptune. Anshuman, you are correct. Nitesh, you are correct. Prince, you are correct. Chaitanya, you are correct. Amrit, you are correct. Perfect. So actually, this is where the things again change. Just like the twist that we had in the hottest planet, there is a twist here as well. That on an average, if you see, on an average, Neptune is colder. But when it comes to the absolute coldest temperature, it has been recorded on Uranus and not on Neptune. And that also has a reason. The reason is that the atmosphere of both of these planets, it is made of methane. All right, atmosphere of both of these planets is made of methane, and that's why you'll see that both of them have bluish color. If you observe the pictures of these planets, you'll see that both of them have bluish color. Now, if you see, Neptune has a dark blue color and Uranus has a light blue color. This dark blue color is mainly because of methane. And this also is mainly because of methane. But Neptune has more methane in the atmosphere than Uranus. Right? More methane in the atmosphere than Uranus, and that is what makes it. It is very very cold. But when it comes to the heat trapping on Neptune is more as compared to Uranus, because Neptune has more methane, and methane also is a greenhouse gas. So that's why it traps more heat. So that's why we see that when it comes to recording the lowest temperature, we have recorded the lowest temperature on Uranus and not on Neptune. So this is again one twist. So the twist that we had in the hottest planet is a similar twist that we have in the coldest planet as well. Now, apart from that, what we see is when we talk about Uranus, there's one more thing about Uranus, that Uranus also has a very unique orbit. What we discussed about Venus is that Venus rotates from east to west. Something similar happens with Uranus as well. But at the same time, what we also observe with Uranus is that Uranus has an axis which is almost horizontal. Right? It has an almost horizontal axis. So most of the planets, including the Earth, they have a vertical axis or maybe a little tilted axis from the vertical. This is the axis in general that we see with all the other planets. But with Uranus, we see that this axis is almost horizontal. It is almost horizontal. So because of that, when it is moving around the sun, it looks like it has been rolling around the sun. It has like a rolling motion around the sun because of the horizontal axis that it has. So that's why we can in a manner say that Uranus has a unique orbit with almost horizontal axis. So looks like rolling around the sun. So this is basically what we see. So that's why again, when we look at these data, so just remember some of these data points, they can become important from the perspective of the examination, because these are some of the things which are unique and very well known. Of course, there are many other facts also that we have about all these planets, but we can't go to all these facts. I don't think that many of these other facts will be as important as some of these things that we are looking at. So that's why these points become important from the perspective of your prelims examination. Just in case they want to ask a question, these are the things that they can ask. All right, these are the things that they can ask you. So now, one more thing, because it was in the news last year, and this is about the number of moons. It is about the number of moons. So last year there was a news about the fact that Jupiter now has 92 planets, right? Jupiter now has 92 planets. Now, sorry, 92 moons, and it has taken over the number of moons that Saturn has, correct? It has taken over the number of moons that Saturn has. So Saturn, until that news, Saturn had the highest number. Saturn had 82 moons in total, and Jupiter had 72 moons. And there were 20 extra moons that were added to the list of Jupiter moons. So now Jupiter became 92, and Saturn remained 82. So now Jupiter became the planet with the most number of confirmed moons. Then after that, there was one more update that happened, and this update was that now a lot of unconfirmed moons that we had for Saturn, that they were also confirmed, and now Saturn has 145 confirmed moons. So now again Saturn has become rank 1, and again Jupiter has become rank 2. I don't think that the exact number will be asked, but you should just know, because this was also it also has been in the news that confirmation for Saturn also has been done, and it was last year that first Jupiter confirmation was done. Jupiter became rank 1, and again now Saturn has taken over. So this is all about planets. So these, some of these things, they will become crucial from the perspective, just in case they have to ask a question, because it has been a while since they asked a question. But as I told you, that last couple of years, they have again started asking questions based on celestial bodies. Right? Any question from here? All fine? All right. Are there atmosphere inflammable due to presence of methane? No, no, no. Only just because of presence of methane, nothing can become inflammable. You need certain criteria to be fulfilled for any kind of combustion to happen. So combustion just cannot happen like that. Even for example, let's say on the Earth also, the atmosphere does have methane, although very small amount, but it does have methane. So from just by having methane or just by having anything that can catch fire, it doesn't really catch fire. You need other criteria to be fulfilled. For example, you need presence of oxygen, you need certain temperature, and all these things. Then only that can happen. Otherwise, not. Huma has an egg shape, still a dwarf planet. Yes, I mean it is, when we say sphere, it need not be a perfect sphere all the time. Even then, we'll be able to call it as a planet. Why outer planets have rings? The reason that has been given is that there are chances that there would have been early celestial bodies on moons, etc., that might have been near these planets, but they might have broken off because of one reason or the other, sometimes because of gravitation, sometimes because of collision. So there might have been various factors, and they just had broken into various pieces, but they kept revolving around this planet. Even it is believed that Mars in future would also have a ring system, that the moons of Mars would break and they would form a ring system around moon in the future. So by future, I mean millions of years. Why Earth is called as the densest planet? Because of the presence of a lot of metals in the solid surface that the Earth has. That's why it becomes the densest planet. Will we be able to complete our syllabus? Okay. Of course we will. The pace is not slow. I mean, if I start going faster, there is no point. Otherwise, everything is written on the slide itself. I can give the notes and go. Right. So let's talk about the other celestial bodies. Now, when we talk about the other celestial bodies, there are others apart from the sun, planet, etc. Three important celestial bodies here, which are very close to one another, where their shapes are also very similar. They look very similar. So you need to understand the basic differences between these celestial bodies. We have comets, asteroids, and meteoroids. So we need to understand what exactly is the difference between these three kinds of celestial bodies. So first we have comets, then we'll discuss about asteroids, and then we'll discuss about meteoroids. Now, first and foremost, comets. Understand that comets, compared to these three, comets are the biggest. Okay, comets have the largest size compared to the others. Now, because comets have the largest size, and when we say largest size, it's not that they're very big or they're comparable to a moon or they're comparable to planets. No, they have a size of, let's say, the radius of a comet would be 5 to 10 kilometers. That's it, 5 to 10 kilometers in radius. Now, the surface will be made of ice, carbon dioxide, ammonia, methane, and there can be other metals as well. There can be metals as well. So core, the surface will be made of all these things. There can be metals, minerals, and again frozen gases, ice, etc., plus dust particles, and all these things will basically make up the core of this comet. And then after that, what we see is that comet also has an orbit around the sun. It also has an orbit around the sun, a fixed orbit around the sun. And when it comes a little nearer to the sun, this is when we see that it starts to heat up, and because of that, it spews dust and gases into a giant glowing head that is larger than most planets. And this is where it also starts to form a tail. This is also where it starts to form a tail that is visible. So comets are known for their tail, right? That you know that comets, one very particular imagery that we have for the comets is how they showcase a tail apart from the body that they have. And one more thing that you should know is that comets have atmosphere. Comets have atmosphere made of hydrogen. Comets have atmosphere which is made of hydrogen. So they have a hydrogen made atmosphere. The size is of a small town. So as I told you, that they have a radius of 5 to 10 kilometers. They have a radius of 5 to 10 kilometers. So these are the things that we should know about a given comet. So compared to that, when we look at an asteroid, asteroids are much smaller. Asteroids are much smaller in size. They might have a size of just 200, 300 meters to maybe 600, 700 meters, and that's it. So they can be even 100 meters, 50 meters in size. So on one hand, we are talking about 5 to 10 kilometers in radius, whereas here we are just talking about 50 meters or 100 meters, or maybe if they are very big, then 500, 700 meters. That's it. So that's why first and foremost they are very small. Secondly, they do not have an atmosphere. So that's why we are saying these are small airless rocky worlds. So small, airless, rocky. These are the three keywords when it comes to an asteroid. So small. So they could be just 50 meters to maybe up to 600, 700 meters in size. Airless because they have no atmosphere. And when we say rocky worlds, we basically see that they could be made of, they can be made of a metal, they can be made of some minerals, they can be made completely of carbon. So they can be made of anything. And because they're very small, it's not that they would have an even out surface, or they would have a mixture of a lot of things. What we'll see is that largely they would be made of one thing or the other only. They'll be made largely of one thing or the other only. For example, they might be made of iron, they might be made of nickel, they might be made of some kind of mineral, they can be completely made of carbon. So we see that all these are possible. It is believed that asteroids, largely the asteroids that we have in our asteroid belt, they might have been a planet in the early part of the solar system. They might have been completely broken because of the gravitational pull from both the sides, from the side of Mars and Jupiter. They might have broken up and they would have remained in this asteroid belt. So this is what is believed about an asteroid. The next one is a meteoroid. Now, when we are looking about a meteoroid, just understand that meteoroid also has a very similar composition, but they are even smaller. They can be just of the size of dust. They can be like just 5 meters or maybe 10 meters in size. So they will be very, very small. They will be very, very small. You can say like stones. They'll be so small. So comets, we know the composition. We know that they revolve around the sun, and they would have a revolution. I mean, they would have an orbit size which is very, very big. Asteroids, they are smaller, made of metals, made of minerals, etc., and they are in the asteroid belt. And they have formed their own belt, and they largely reside there. And meteoroids, they will be even smaller. They'll be very, very small, size of a stone, and they would not have a fixed path. They may not have a fixed orbit. They might just keep on hanging around the space. And this is where we see that this is where they would be made. They would be very, very small as well. So they range in size from the size of dust to around just 10 meters in diameter. So small, and they can be made of iron or some kind of stone, or they can have extraterrestrial nickel. All these things can be present in a meteoroid. Now there are other terms as well that we have here. We have meteors and we have meteorites. So what do we mean by meteorites and what do we mean by meteors? So when it comes to these kind of terms, just understand that they're all meteoroids only. But when a meteoroid, it comes near the earth, right? When it comes near the earth, what happens is that it will be pulled by the gravity of the earth. So as it is pulled by the gravity of the earth, it will start falling on the earth. But while it falls on the earth has a very thick atmosphere. So because of that, there will be a lot of air friction and it will be completely burned up. It will completely burn up in the atmosphere of the earth itself. In that scenario, it will be called as a meteor. In that scenario, it will be called as a meteor. So almost you can say more than 99.99% of all the meteoroids that come to the earth, they completely burn up in the atmosphere, and hence in that case they're called as a meteor. But then you also have meteorites. Now meteorites are when a meteoroid, while traveling through the earth's atmosphere, does not completely burn up. Right? It does not completely burn up, and maybe a very small speck of dust or maybe a very small stone falls on the surface of the earth. And if that happens, then in that case it is called as a meteorite. All right. So that's why a meteorite that burns up as it passes through the earth's atmosphere is known as a meteor. So this happens because of air friction. And then a meteorite that survives the falling through the earth's atmosphere and colliding with the earth's surface is called as a meteorite. So this is where it does not completely burn up. So this is how we basically look at the things. Meteoroids, the ones that you have in space, meteor in our atmosphere, and as it completely burns up. And if at all it falls on the earth, then in that case it is called as a meteorite. So when it comes to the meteoroids or meteorites or meteors, it is believed that the falling of meteorites on the earth might have led to the extinction of dinosaurs on the earth. And you might know that when you see a meteor in the sky, many also believe that if you make a wish, when you look at a falling star, it is also called as a falling star or something like this. But when you see a meteor falling through, and if you make a wish, then your wish comes true. And this happened for dinosaurs. That this might have happened for dinosaurs, that they might have also wished for the same. So what we believe is that this event is also called as a mass extinction. This event on the Earth's geology is also called as mass extinction. So mass extinction is when a lot of flora and a lot of fauna that lives on the earth, they all die or they all lose their lives in a very short span of time. Then in that case, it is called as a mass extinction. So what might have happened in case of dinosaurs as well is that there might have been meteorites that might have fallen on the earth. A lot of them might have fallen on the earth, and because of that, they might have created a huge impact. They would have created a huge impact, killing many. And apart from that, a lot of dust particles, etc., might also have been spewed while the impact happened. And because of that, a cloud of dust would have been made in the atmosphere, blocking the sun for a very, very long time, a significant amount of time. So that blocks the sun. Blocking the sun means blocking photosynthesis. Blocking photosynthesis means that the plants would not survive. Plant not surviving means that the other animals, etc., which are surviving on them, they would have also completely gone, or they would also have lost their lives. And it is believed that almost 85% of living organisms, including the dinosaurs, they died. 85%. So that's why we have to understand that this basically this is something that would have happened at that point of time. So at this point of time, almost 85% of the lives were lost. And today, when we talk about mass extinction, today we say that there is the sixth mass extinction going on. Have you heard of this term, sixth mass extinction? So any idea what this sixth mass extinction means? Yes, correct. Ilma, you are correct. Saloni, you are correct. Nitesh, you are correct. So what we mean today is that until now, we say that there are 5 mass extinctions that have happened on the earth. 4 of them have been because of the natural climatic changes or cyclic changes that keep on happening on the earth. 1 of them has happened because of external factor, which is this, that the falling of meteoroids led to this mass extinction. So I'll just write here falling meteorites led to mass extinction. So four of them would have been because of the cyclic changes that happens in the climate of the Earth, and one of them has happened because of a external condition, that is falling meteorites. Now, in this, we say that today we are going through sixth mass extinction, and what we mean by sixth mass extinction is that all of these until now have been natural factors, but this time it is happening because of the action of humans. This is happening because of action of humans. That the way we have progressed, the way we have been destroying the environment, we have been destroying the living conditions, not only for ourselves but for every other flora and fauna as well. It is leading to the sixth mass extinction, that there is another mass extinction going on right now. Now understand that if mass extinction does not mean that everything has to die within a year, or all the flora and fauna should die in 10 years or 20 years and so on. No, it could take 1,000 years. It could take 1,000 years. So 1,000 years compared to the geological history of the Earth is nothing. It's a very small period. That is 1,000 years, given the geological period that you have for any planet, not only for the Earth. So that's why 1,000 years does not matter a lot. So because a lot of people say that there are hardly some extinctions that have happened over the past 20 years. How do you say that there is a mass extinction going on? There are a lot of events that we see. There are a lot of evidences that we have. So for example, let's say the evidence is that the amphibians give us. It is said that some of the amphibians, they are the most sensitive of all the fauna that exists. Frogs, for example, frogs are said to be one of the indicators of mass extinction, because frogs they lose their lives very easily with smallest amount of change. Same is said for the corals as well. We know about the corals also, that how very fast they can lose their lives. So there are some of these indicators. These are indicator species that indicate that these kind of events are happening. So that's why sixth mass extinction as a topic in environment and ecology rather is an important topic for you. Look at this question. Please read this question. This was asked in your paper. Read this question and then I'll launch the poll also for you. Alright, so if you've read the question, I'm launching the poll now. I'll give you 30 seconds. Please mark your answers. Alright, so 53% of you have marked B, which is the correct answer. Let me just discuss this with you. What is the difference between asteroids and comets? First, asteroids are small rocky planetoids. We discussed about this. While comets are formed of frozen gases held together by rocky and metallic material. So we discussed that minerals, rocks, dust, ice, and various different gases, frozen gases, all these are there. So this is perfectly correct. Asteroids are found mostly between the orbits of Jupiter and Mars. This is fine. While comets are found mostly between Venus and Mercury. No, we never discussed this. And what I also told you, that they have a very big, right? They have a very big orbit, so they can't be between Venus and Mercury. They can't be so near. Otherwise, I mean, for example, comets for us are visible, many of them once in 80, 90 years. Halley's comet, the most popular one, once in 76 years. So obviously, they have a very big orbit. So that's why they can't be found between the orbits of Venus and Mars. And we never, sorry, Venus and Mercury. We never discussed this. Comets show a perceptible glowing tail. This is correct. While asteroids do not. This is also correct. So 1 and 3. This was an easy question. Second option is easy to mark as wrong because of this one thing about Venus and Mercury. Then we come to the edge of the solar system, where we have something called as Kuiper belt. Now, when you look at the Kuiper belt, what you see is that this is a belt, this is a wide region just after Neptune, where we see that a lot of small celestial bodies are found here. A lot of dwarf planets are found here. A lot of comets are found here. A lot of smaller meteoroids are also found here. Some asteroids are also found here. So there are all these things that are found in this particular area. It is called as a Kuiper belt. Now, what's special about this belt is that now you have come very far away from the sun. So because of the distance from the sun, the gravitational pull of the sun is limited as compared to what it used to be in the inner part of the solar system. And that is the reason why so many smaller celestial bodies can very easily survive here. They can easily survive here because the gravitational pull of the sun is not so strong. If the same celestial bodies were in the inner part, then they might not have been able to survive. They might have been pulled by the sun. But this is not what happens here. So this is what we see. The distance here starts from 30 to up to 55 astronomical units. Now, when we say astronomical units, do you know how much is one astronomical unit? How much is one astronomical unit? Anyone? Yes, distance between the sun and the earth. Correct. So this is almost 150 million kilometers. Almost 150 million kilometers, which is the distance between the sun and the earth. So this is called as one astronomical unit. So here we are saying that it is 30 to 55 astronomical units, meaning that we have come almost 30 times the distance between us and the sun. All right. So 30 to 55 astronomical units. So what we see here is that many small celestial bodies reside here as the gravity of the sun is weaker now. All right. So that is why many small celestial bodies reside here. So what all? You have the dwarf planets. You have a lot of comets. You have a lot of meteoroids. So all these smaller ones, they can exist in this particular region. Then after that, we have the edge of the solar system called as the Oort cloud. Now, in case of Oort cloud, we say that it exists between 2,000 to up to 2 lakh astronomical units. 2 lakh astronomical units. It's a big space that we are talking about, and it contains a lot of things. For example, it contains a lot of frozen things. For example, ices such as water or methane, ethane, carbon monoxide, hydrogen cyanide, etc. They all might be present in this region, and this is theorized that they might be present in this region because it's too far away from us to even comprehend what exactly would be the exact nature of the composition of this area. So the solar system would end, the Kuiper belt would end, and ultimately after that we would have the Oort cloud. So Oort cloud, in a manner, you can say, becomes the boundary. It becomes the border between one solar system and another star system. So once Oort cloud happens, planets. Then after that, you might have other stars, and they might have their own solar systems, and they might have their own planets. And these kind of planets, as I told you, they would be called as exoplanets. So all these are the things that we see. And for these exoplanets also, I mean, what we see, okay, there is one question that has been asked here. Just look at this question first quickly. There was this question asked: the term Goldilocks zone is often seen in the news in the context of what? Oh, so sorry, so sorry. Oh, this leaderboard is going to be wrong today. I by mistake marked A. The correct answer actually is C. And all of you, 45% of you had marked C. You were correct. I don't know. I don't think that this can be done right. But yeah. So sorry for this. So the term Goldilocks zone is often seen in the news in the context of. So Goldilocks zone basically is the zone where there are chances of finding life, where you have moderate temperatures today. Sorry, all right. So for example, let's say when you talk about the sun, there is a certain distance from the sun where the temperature is neither very hot nor very cold, and Earth thankfully lies in this region, and that's why life on the Earth exists. Same, that's why we say about Venus also, because Venus also lies in almost that Goldilocks zone for this for our solar system. But there are internal conditions because of which life does not exist on Venus. Otherwise, Venus also could have sustained life if not for other conditions. So Goldilocks zone is the area beside any planet, sorry, beside any star where there are chances of finding life because of moderate temperatures. So area around a star with moderate temperature increasing the chances of finding life. All right. So first is limit of habitable zone. Habitable zone is fine, but not above the surface of the Earth. It's anywhere in the universe. Then regions inside the Earth where shale gas is available, nothing to do with it. Search for Earth-like planets in the outer space. So that's why, because we are looking for that habitable zone. Search for meteorites containing precious metals, nothing to do with any meteorites. So that's why this is search for Earth-like planets in the outer space where we are looking for moderate temperatures where chances of finding life are high. Now this question was asked in 2015. Basically, it was also, you can see that in a manner it was more of a current affairs question, because there was a mission called as the Kepler mission. There was a mission called as the Kepler mission, and this Kepler mission was going towards the outer solar system in search of a lot of in search of all these kind of planets. So that's why this kind of mission was also launched. So in all these cases, we have seen that. So that's why it was more of a current affairs question that UPSC had asked. So this is the first part. This is the first part where we have discussed about space, we have discussed about the universe, the celestial bodies, and space science in general, you can say. Now, this is a part, until now, whatever we have seen, this is a part which is more important from your prelims perspective than mains. But now we enter the second part, and this is a part perhaps where both prelims and mains based questions can be asked. So we are entering space technology now. Now, to understand space technology and how the observations are made, first we have to understand what are the various ways in which we make the observations. So there are two basic ways in which we define the observations that we make. One called as ground-based observation, and second called as space-based observation. So when we say ground-based observation, it means that we are sitting on the ground and making the observations. That's why this is called as ground-based observation. Now, in this particular scenario, what we see is that we are using the telescopes. We are making the use of telescopes, and with the help of telescopes, we are looking at the outer space. Now, when it comes to telescope, what we know about the telescope is that telescope will give us images. It will give us pictures, and you will be able to see through the telescopes. Now, to see through the telescopes, it's not that you will always see what you want to see. There are, understand that when we talk about images, when we talk about taking images, you can take an image in any part of the electromagnetic spectrum. Okay, so just to give you a brief here, when we talk about the electromagnetic spectrum, you can take an image from any part of the electromagnetic spectrum. So you have various different types of electromagnetic waves. We have radio waves, we have microwaves, we have infrared rays, we have the visible light, ultraviolet, X-rays, gamma rays. We have all these, correct? All these are called as electromagnetic radiations. You can take any one of these to take the images. Does that how we perceive images is only through the visible part, and that's why what we see through the visible light is very different from what we might observe with the help of other waves or other radiations. What we see is that when it comes to the telescopes, the optical telescopes and the radio telescopes, they are the most widely used. So it's not that we can't have an infrared telescope. We have the James Webb Space Telescope, which is an infrared telescope. There can be X-ray telescope. Our own AstroSat was also an X-ray telescope. So that's why we can have any kind of telescope based on any part of the electromagnetic spectrum. But the most widely used are optical telescopes and radio telescopes. Now, why exactly is this? Why optical? Because optical telescopes, they use the visible part of the electromagnetic spectrum, right? They use the visible part of the electromagnetic spectrum, and because of this, because they use the visible part of the electromagnetic spectrum, that's why the images that you capture through an optical telescope is very similar to how we perceive the world, right? How we perceive the world is very similar to what we get, or the images that we get through an optical telescope. Now, when it comes to the optical telescopes in India, we see that they are located in Devsthal in Uttarakhand, in Hanle in Ladakh, and in the Javadi Hills in Tamil Nadu. So these are the three areas, three places where optical telescopes of India have been placed, and the most famous one in all these three has been the one at Hanle. Now, Hanle, you have to understand that you might have also heard this was in the news last year as well for Dark Sky Reserve. Heard of this news? That this place now is called as a Dark Sky Reserve. And why do we say that it's a Dark Sky Reserve? Any idea? Why have we called this area as a Dark Sky Reserve? Free from light pollution. That's correct. Clear skies, right? Yes. Can we visit places where optical telescope is located? Yes, we can. I'll tell you about this. Yeah. So no light source. So basically, why Dark Sky Reserve? Hanle, just understand Hanle. And this telescope that you see, this picture of the telescope that you see, is the picture of the Hanle telescope. All right. And this is a picture that I have taken. This is not a Google image. This is an image that I have taken. I have been to this telescope. Now, So, and I have been to Hanle. So, going to Hanle, I understand that why dark sky reserve. Why is it being seen as a potential site for dark sky reserve? What is a dark sky reserve? Dark sky reserves are areas which have a potential for very good stargazing. That this is where you can very easily watch the night sky, and the images will be outstanding. They will be wonderful. So, you can't compare it to the images that you might see from a city, whether a metro or even the other cities of the country. So, compared to that, these are areas which have clear night skies. They are away from light pollution. They are away from any kind of population settlement, any kind of air pollution. And because of that, the night view that you have is wonderful. And that's why they want to conserve it as a dark sky reserve, so that people can come here and can also become a kind of tourism that people come here just to stargaze, just to watch the night sky. Now, I went to Hanle. So, Hanle it is a place in Ladakh. From the city Leh also, it is pretty far away, almost 200 kilometers away from it, almost near China border. So because of that, a few things that we see, it's a cold desert. All right, it's a cold desert, so hardly any rainfall. For Hanle, what we see is that it has more than 300 days, of cloudless skies. No clouds for more than 300 days in a year. Hardly 2 or 3 days of rainfall in a year. Even not that in some time, some time in the year. Sometimes we see that not even a single day of rainfall happens. So almost no rain, clear skies, no clouds, almost no human settlement. Very difficult to reach. For example, if you want to go to Hanle, there is only one bus that goes from Leh to Hanle, and only one bus that comes back in a week. So if you have to go every Saturday, there is one bus that leaves from Leh and goes to Hanle, and Sunday it comes back. So that's the only thing. And otherwise, if not bus, you can take a cab, and the cab can ask you for like rupees 20,000 or so for going and coming back. So it will be very costly for you. So that's why going there, reaching there is not easy. It hardly has any water. I mean, they're almost devoid of water. No, the temperatures are very low. I mean, for example, I went in the month of November, almost November end, and the temperature then was, I mean, the day temperature, this bright sunlight, was minus 15 degrees Celsius. So minus 15 to minus 20 degrees Celsius was the temperature back then. So temperatures are very harsh. People hardly live there. Only a small human settlement. People don't visit because it's not easy to visit. So because of all these reasons, we see that this becomes a potential candidate for the dark sky reserve, and that is the reason why it has been named so. I also went inside this telescope. They also showed me around and how exactly the observations are made through this telescope. So this is about the optical telescopes. Now, apart from the optical telescopes, we also have the radio telescopes. Now, when it comes to the radio telescopes, they will capture the invisible radio waves. So we obviously cannot see radio waves. We don't see radio waves, but radio waves have the longest wavelength. And we'll discuss more about it when we go to IT and communication chapter. They have the longest wavelength, so that's why they can make the observations very easy for us. They make the observations very easy for us. So that is why we see that radio telescopes are also very famous. There are two in India which are very popular. One located in Pune and one located in Uti. So these are the two radio telescopes that India has. Now, if you look at the radio telescopes and if you look at the optical telescopes, you see that the images that you get are very different. I mean, for example, when you imagine Jupiter, what you perceive Jupiter as is this, the second image that you see. This is how we would see Jupiter if we could directly see Jupiter, right? So this is how it would look like. But when you look at the radio image of Jupiter, you see that it's completely different. This is not how you perceive Jupiter, right? So that is how we understand that there is a difference between how you get the images. Now, those images can be processed. That even the images that you get from radio telescopes or infrared telescopes, they can be processed for us to understand how they would look like through given what we have observed. So we can actually process those images. For example, a lot of James Webb Space Telescope images that we have been getting, these are images that are processed images. That first the image that we captured was in infrared rays, and then after that those infrared images were converted to optical images, the images that we can understand. So this is about the ground-based observations, but more important than this is about our space-based observations, where we are launching a satellite, and this satellite basically the satellite will be used for making observations or even being launched for any of the applications that we need from the satellite. The basic idea behind the launch of any satellite is Newton's first law. What does Newton's first law say? Newton's first law says that an object in motion remains, object in uniform motion remains in uniform motion, an object at rest will remain at rest until acted upon by an external force. That until an external force acts upon it, until that point, it will remain in at rest, right? Or if it is, let's say, a uniform motion, it will remain in uniform motion. So this is what we say about the first law. So now what? So that's why the object in motion will stay in motion unless something pushes or pulls on it. And this is basically what we get from Newton's first law. So Newton's first law is one of the driving factors when it comes to launching a satellite into an orbit. Now, overall, when it comes to launching a satellite, just understand the basics of what we are doing. So when we are talking about Newton's first law, why are we talking about Newton's first law? That object at rest remains at rest, object in motion remains in motion unless acted upon by an external force. Now, Newton's first law basically talks about balancing of forces. It talks about balancing of forces. So what happens is that, let's say, even if you have, let's say you have a small box which is lying on a surface, then you start pushing it in one direction. Let's say there is one person pushing it in this direction with 10 Newton force, and there's another person who's pushing this block from this direction also with a 10 Newton force. Then in that case, what happens? That this box will remain where it is. Correct? It will remain where it is. So now what happens is that if, let's say, this person one increases this force to 12 newtons instead of 10, and this remains 10, then in that case, what happens? It will start moving in this direction, right? So what happens is that until the point you have unbalanced forces, the motion will happen in one direction. As soon as you have forces balanced from all the sides, it will remain in its place. Now, when you compare this to what happens to a satellite, so in case of a satellite, what we see is that, let's say we are launching a satellite. So suppose that this is a satellite. Now, this satellite will be facing a very strong gravitational pull from the Earth. So this is one force that you have. Now you have to counterbalance this force. Correct? You have to counterbalance this force, and if we are able to counter this force, only then we will be able to put this satellite into the required orbit and ensure that this satellite remains in this orbit. Because otherwise, what happens is that if one of these two forces, either the gravitational force or the other force due to motion, if either of these two forces are greater than the other, then the motion will happen in that direction. Okay? So for a satellite to remain in its orbit, the forces on it should be balanced. Right? The forces acting upon it should be balanced. And what are these two forces? So here we have the force of gravitation. On one hand, you have gravity, and on the other hand, you have force due to motion or the circular motion that that this satellite has. So overall, what happens is that there are two forces that are acting upon it. One is called as the centripetal force. One is called as the centripetal force, and the other one is called as the centrifugal force. Centrifugal force. So these two forces have to be equal. One is called as the centripetal force, one called as the centrifugal force. So centripetal force in general is the force that acts towards the center. Right. So this basically acts towards the center, and this force acts away from the center. So this basically, so the first one basically is the force of gravitation. This is gravity, and this is force due to circular motion. So as long as these two forces are balanced, on a given satellite, the forces, as long as they are balanced, it will remain in that orbit. So this is how we launch the satellite. To launch the satellite, what we have to do is that let's say a satellite has to be launched to 1,000 kilometers. So we want that it should have an orbit of 1,000 kilometers around the Earth. So if we want the forces to be balanced at 1,000 kilometers, then in that case we have to do a calculation in a manner that the forces, the force that we are exerting, but basically the launch that we are doing, the thrust that we are providing, it should be able to balance the gravitational force at 1,000 kilometers. So this is how the calculation will be done. But it's a simple case of balancing the forces. So as long as the forces are balanced, you can keep the orbit or you can keep the satellite in its orbit. But in practicality, things are not as simple as it seems here, because there are a lot of factors. For example, let's say first and foremost, this entire system is not a circular motion. Most of the times it is elliptical in nature, so that is one problem. Then there is the air friction as well. We are not counting that. That's another problem. The satellite that we are launching, it also has a finite mass. We are not counting that. As it goes up, its mass also changes because fuel will keep on being consumed, and that's why the weight of the satellite keeps on decreasing. That also becomes a problem. So there will be pull from other celestial bodies also. That also is a problem. So the Earth is not a complete sphere. That also is a problem. So there are a lot of these kind of problems. All right, there are a lot of these kind of problems. So that's why it's not as easy as it seems. There's a reason why rocket science is called as rocket science. Rocket science is something, I mean, anything that is difficult, we say that it is rocket science. So why do we say that? Because rocket science is supposed to be difficult. It's one of the most complex of the technologies that humankind has mastered. So that is what we see. So the forces have to be balanced. And as long as the forces are balanced, you can keep the satellite in the given orbit. Now, there is this one interesting question that has been asked, and also a difficult question, I would say. It's not an easy question, but it has been asked in your paper. It was asked in, I think, 2012 paper. This question was asked. Just go through the question. I'm also launching the poll for you. And then please mark your answers. Right? I hope you've read the question. I'm launching the poll. Please mark your answer. So 5% of you have marked A, 20% B, 27% C, and 47% D. All right. So the question says artificial satellite orbiting around the Earth does not fall down. This is so because of attraction of the Earth. A does not exist at such height. Is it even possible? It's not possible. The launching of the satellite, what I'm telling you is that the force of the Earth has to be balanced. You cannot say that it does not exist. It does exist. We have to balance it. It is neutralized by attraction of the moon. It can't be neutralized by the attraction of the moon. Moon is very far away, and moon has a very small gravity, almost 1/6 gravity compared to the Earth. So that's why moon cannot do anything. And moon is very far away. Do you know how far moon is? How far is moon? Anyone who knows? Yes, 3,84,000 kilometers. So just imagine we are talking about 3,84,000 kilometers, whereas you are launching the satellite just 500 or 600 kilometers away, or 1,000 kilometers, maximum 36,000 kilometers, whereas moon is at 3,84,000 kilometers. So that's why moon cannot neutralize anything. So now coming to C and D. C says provides the necessary speed for its steady motion. D says provides the necessary acceleration for the motion. So speed is correct or acceleration is correct? The correct answer will be acceleration and not speed, and I'll tell you why. Can you tell me the formula for force? What is the formula for force? A simple formula for force. Yeah, mass into acceleration. Mass into acceleration. So when we are talking about balancing of the forces, now in the balancing of the forces, what happens is that you have two parts to it. So when it comes to mass is something that we know, correct? Mass is already a known factor for us. Acceleration is what we have to calculate. Acceleration is what we have to provide for the launch of the satellite to happen, and it's not speed, because also realize this, that the motion of the object is such that we are trying to give it an acceleration so that it can go to the required height, and only providing the speed is not enough. Speed with direction is required, correct? So it's not only necessary speed, but rather necessary velocity. More than speed, it is more about velocity. And what do we mean by velocity? What is the difference between speed and velocity? That velocity is speed plus direction. When you are defining speed in a certain direction, you say that it is velocity. So direction matters here, correct? Direction matters, and it's not only about speed. If let's say option number C, instead of speed, would have said velocity for its motion, then it would be a difficult answer. But it is not a steady motion. It will keep on changing every second because it is a circular motion. So velocity keeps on changing every second. So that's why what we actually give is necessary acceleration for the motion and not the necessary speed. So that's why it's a difficult question. I'm saying I agree that it's not an easy question, but they have actually asked this question. Break will take at 7:45, right? Almost at 7:45, we'll take the break. So let me just continue for 10 more minutes. Now, coming to the understanding of orbits, what we now have established is, okay, fine, we need to provide a certain acceleration, we need to balance out the forces so that we can keep it in a given orbit. Now, when it comes to the understanding of the orbits, there are two scientists whose contributions are very, very important. One, Kepler, and second, Newton. So first, we started with Kepler because Kepler gave 3 laws of planetary motion, and then Newton came later, and Newton said that whatever is applicable on the planets, the laws given by Kepler, the ones that are applicable on planets, they are not only applicable on planets, they can be applicable on any two-body system in the entire universe, wherever one body is revolving around the other. So what Kepler did what Kepler did, Kepler gave three laws, and these three laws were based on observations, based on the observations of the planets, the movement of the planets, all these observations, the observations which were not made by Kepler, but rather the teacher of Kepler, the mentor of Kepler. He actually had made a lot of observations, and he had made a note in a very thick journal that he had. And these journals, while they were being studied by Kepler, Kepler saw a pattern that the teacher had not seen, a pattern that his pupil Kepler had seen. And then Kepler started working more on that. He kept on observing more. He kept on working on that data, and ultimately he came to a conclusion that there are three patterns that he saw, and these three became the laws of planetary motion. So these were, you can say in a manner, observations about the motion of planets around the sun. What kind of observations? First, all planets move in elliptical orbits with sun situated at one of the foci of the ellipse. Second says planets sweep out equal areas in equal times. We'll discuss this. Third says orbital period squared is proportional to the size of semi-major axis cubed. So it looks to be a very complex law, but I'm telling you it's a very simple law. We'll come to that and you'll understand that it's a very simple law. What the first law says is that planets orbit in ellipses with sun at the focus. Now what is an ellipse? You can say kind of an egg-like shape. Something like this can be called as an ellipse. Now focus, there are 2 points in any ellipse that are called as focus. There are 2 axes also which are called as the major and the minor axis. So this is a typical shape of any given ellipse. It can be very highly elongated, it can be kind of circular, and circle also, I've not drawn a perfect circle, but circle also is called as an ellipse. It's a special case of ellipse where these 2 axes, the major and the minor axis, this one is called as the major axis and this one is called as the minor axis. So when these two are equal, what happens? It becomes the diameter of the circle. It becomes the diameter of the circle. So this is basically what we see here. All right, this is what we see, that circle is a special case of ellipse where minor and the major axis are equal. And to define how elongated this ellipse is or how circular this ellipse is, we have a factor which is called as E, also called as eccentricity. We have this one thing called as eccentricity, or denoted by E. So E for an ellipse lies between 0 and 1. It will be less than 1. It can be up to 0.99999 and so on, but it cannot be 1. So, and when it is 0, it is a circle. Right? When it is 0, 0 basically is a circle, and this, let's say 0.9999 and so on, this is a highly elongated ellipse. Highly elongated ellipse. So in this case, what we see is that this is how he says. What he simply says is that whatever kind of ellipse it is an ellipse. The planets, their orbit is elliptical in shape, is what he had concluded in the first law, and he said that the sun lies at one of the foci. That this is where the sun lies, or this is where the sun lies, and so on. Then in the second law, what he says in the second law is that planets sweep out equal areas in equal times. So equal areas in equal time meaning that equal time. If you look at this, this is a total period of 10 days, and this is also a total period of 10 days. Correct? Both of it, they are 10 days. So in case of 10 days, what it is saying is that equal areas are being covered. So this area and this shaded area, the blue colored area, these 2 areas are equal because the time period at both the ends are equal. Now what we observe and where this law comes from is that when a planet is near the sun, because when it is near the focus, when it is near the sun, it moves faster. It moves faster. When it is away from the sun, it moves slower. So towards the sun or close to the sun, fast; away from the sun, slow. So this is where the observations came from, and this is where, when he calculated, he saw that the area being swept in a given period of time is always equal wherever it is. So always, if we are taking, let's say, a 10-day period, the area being covered will always be equal. So the observation basically, the conclusion from here is that the planets move faster when closer to the sun, and planets move slower when away from the sun. So faster when closer, slower when away. And this is a very, very important law which also has an application in making the satellites, in launching the satellites, and we'll discuss about that later. But we do see that even in launching satellites, we use this law. Then comes the third law, which looks to be a very typically technical law, but it's very easy. It says orbital period squared is proportional to the size of semi-major axis cube, something like this. Now just remember that what it essentially is saying is that if there is a planet which is near the sun, it will take less time to complete one revolution, and when you have a planet which is away from the sun, it will take more time to complete one revolution. So this goes without saying, right? You would say that this is common sense, but this is common sense today. In 1600s, if you had this common sense, the law would be named after you. So, but he mathematically proved that this exactly is the relation between the size of the axis and the time it takes to complete the orbit. So this is what we see, that for example, Earth takes 365 days almost to complete one revolution, whereas when you look at Pluto, Pluto takes 238 years to complete one revolution. Why? Because Pluto is far away, so it takes more time. Earth is near, takes less time. In a manner, you can say that it also gets derived from the second law, because in second law, what we also said was that when the planet is near the sun, it moves faster. When it is away from the sun, it moves slower. So in a manner, you can say that this third law also comes from there. So very simple laws. For Kepler, these laws were applicable on the planets. These laws were applicable on the planets and nowhere else. But then came Newton, and Newton gave something called as the universal law of gravitation. Universal law of gravitation. And after universal law of gravitation was given, now we knew that gravitation, gravitation exists between any 2 bodies in the universe which have mass. So what then happened is that all these 3 laws, which were only applicable on planets, now they can be applicable on any 2-body system where one body is revolving around the other body. So wherever you have something like this, these 3 laws will be applicable there. So now these 3 laws that we knew until now only for the planets, now even in launching the satellite, we use the same laws. The same 3 laws are applicable even on a normal satellite that we launch. Any satellite that we launch also will be governed by the same 3 laws. All right. So this is basically where we understand that he had given a basic understanding of how exactly we look at the orbits. So there are 3 types of orbits that we define on this basis. There is a low Earth orbit, medium Earth orbit, and high Earth orbit. So understand the basic meaning of it. Low Earth orbit meaning that this is an orbit which is near the Earth. So starting from almost 180 kilometers going up to 2000 kilometers, we call it as the low Earth orbit, because this is basically the orbit which is near the Earth. All right, this is the orbit which is near the Earth. Mid-Earth orbit starts from 2000 kilometers, goes up to 35,786 kilometers, and high Earth orbit is at or above 35,786 kilometers. Now, why this specific number? Why 35,786 kilometers? The reason for this is that this is the height where time period of revolution, where orbital period is of 24 hours, meaning that it takes 24 hours for a satellite at 35,786 kilometers to complete one revolution. What is the significance of 24 hours? It is also the rotational period of the Earth. Correct? Earth takes 24 hours to complete one rotation, and this revolution takes 24 hours. So then what happens is that when you keep, just remember this, that when you keep any satellite which is at 35,786 kilometers, it revolves as the Earth rotates. So with respect to a point on the Earth, it always remains stationary. It always remains stationary, does not move when compared to a point on the Earth. That's why this number is significant, 35,786 kilometers. We'll study more about it when we go to these individual types of orbits. So let's take a small break here. The time is exactly 7:45. If you have any questions, whatever we have discussed, because now we have entered a part which is a slightly more technical part as compared to whatever we have been discussing. So it needs your concentration. If you have any doubts with regards to whatever we have discussed, please post your questions. When we come back from the break, I'll take your questions, and then after that we shall move forward. So the time is 7:45. Let's be back by 8, and then we'll have the further discussion on this topic. Welcome back, everyone. Let me take your questions first, and then we shall proceed. Do we need to learn the facts given in the PPT, or do we need to learn more from any book or newspaper? No. See, everything that is in the PPT is relevant. Everything that we have, that I have kept here, plus the additional things that I'm writing here, it's relevant. Anything that is not relevant, I've never written it, I've never used it. But yes, you have to add current affairs to it. So yes, newspaper apart from this will be important. Books not required. How come meteorites size is of dust particles, but when they collide with planet or the Earth, creates a huge impact on it, like of a lunar lake or mass extinction? See, we say that it starts from a speck of dust, but it can be a little bigger in size also. So what happens is that in general we say that they can be up to 10 meters in size. So 10 meters is also big size, and especially when it comes to impact. Understand that when it comes to impact is also about the acceleration that it has, because it will also be pulled by the gravity. So because it is being pulled by the gravity, the acceleration is very high, and because the acceleration is very high, the velocity with which the impact is happening is very very high. The momentum that it carries is very very high, because of which the force that it exerts is very tremendous. That even if you see, for example, there have been cases very recently, just 4 5 years back also, you see that there was a meteorite that came very close in Russia. There are videos available on YouTube if you go there, and you'll find that even though it did not have an impact on the Earth, it did not really fall on the Earth, yet there were impact, or there were vibrations that were felt. There were windows that were broken just because it came very near. So imagine the situation when something which is 10 meters in size, it actually fell. It would have a huge impact because of the momentum that it is carrying. If comets revolve in their respective orbits, how can they come closer to the sun? Because it's an orbit. So for example, let's say this is the orbit and this is where the sun lies. So they would come close to the sun when they are here. How do spaceships make artificial gravity? No, they don't make artificial gravity. They have their own mass, and wherever you have mass, you have gravity. Do comets do comets, asteroids, and meteoroids also have gravitational force? Of course they have. What is the formula for gravitational force? G m1 m2 by r squared. M1 and m2 being the masses, and r being the distance. So wherever you have a mass, you have a gravitational force. Always remember that gravitational force is dependent on mass. Whether the mass is big or small will determine what kind of gravitational force it has. Can you please repeat the third law? So in the third law, what we are simply saying is that a planet which is nearer the sun will take less time to complete one revolution. The planet which is far away from the sun will take more time to complete one revolution, because the planet which is near the sun is completing lesser distance, right? It has lesser distance being covered, and the planet which is far away is covering more distance. More distance means more time. And anyway, we know from second law that anything that is nearer will be faster, anything that is farther will be slower. So that's why the planets which are farther away will take more time to complete one revolution as compared to the ones that are nearer. Please quickly elaborate the first law. So see, in the first law, what we are saying is that all the planets are in elliptical orbits. All right, the shape of the orbit is elliptical, and there are these points which are determined on any given ellipse, called as the focus. So focus is where the sun lies, and planets have an elliptical orbit. This is what the first law is saying. While reading the additional material, it's getting a little confusing. Okay, can you elaborate on that? Because if there is something that I need to discuss with the team, I can do that. How G was predicted? See, the prediction of G basically happens on the basis of the proportionality of the masses that we have seen on any two given masses. So because we know that it is the force is directly proportional to the masses and inversely proportional to the square of distance between these two masses. So this is what we know about the force. And then when we are looking at experiments, these are, I mean, whenever you look at any constant, whether it is the gravitational constant or any other given constant in physics, these are all determined experimentally. That we conduct various experiments with various masses and we try to determine the value of this particular G. The third criteria to be a planet. The third criteria is saying that the planet should have cleared its orbit, or it should have cleared its neighborhood. That there should not be anything in the vicinity. If there is something, it should be revolving around the planet. It should not have an independent existence. All right. If there is a celestial body in the surrounding areas of this planet, it should not have an independent existence. It should either be a moon of the planet, or it should not exist at all. So the gravitational force of this planet should be good enough that it has cleared its neighborhood. How to prepare science notes? See, notes, either you can be dependent on everything that is there on the PPT plus the additional things that I write here, or if you want, you can also make indicative running notes along with the class. Last line on the orbit, high Earth, 35,000 kilometers, not understood. So what I'm saying here is that when you have this height, when the height is 35,786 kilometers, then the orbital period, or the time period it takes to complete one orbit, is of 24 hours. So 24 hours is also the rotational period of the Earth. So that's why any satellite that is at 35,786 kilometers will be fixed with regards to a point on the Earth, because as the Earth rotates, this point is also revolving. So this is what is happening, and because of that, what we see is that the relative position between these 2 points will always be fixed. Right. So let's move on. Okay, so there's also one announcement that the recordings of the classes that we are conducting, the live classes recordings, they will be available for a week's time. That after this class, for example, going forward from the 1st of September, every class that is being conducted, after that, for the next 1 week, the recordings of this class will be available. So I think until now, the recordings are available for a longer duration, but now going forward from the 1st of September, the recordings of these live classes are going to be available for 1 week's time. So just note this. This is what I've been told, and this is something that we are going to do going forward. That the recordings are going to be available for 1 week from the time of the from the live class that we are conducting. All right. So coming to the factors that determine the orbit. So what we know is that there are three basic types of orbits: the low Earth orbit, the medium Earth orbit, and the high Earth orbit. Now, low Earth orbit up to 2,000 kilometers, medium Earth orbit after 2,000 kilometers up to 35,786 kilometers, and then the high Earth orbit at or above 35,786 kilometers. Now, how do we determine the orbit? There are three criteria. Alright, there are three criteria, or there are three factors based on which any orbit is determined, and these things are very very important. These three factors are very very important when it comes to any given orbit. So now, when it comes to these factors, there are three major factors that determine what kind of orbit it is, and largely these are factors that are determining the kind of orbit. First such factor is height. Now, how exactly height of an orbit determines something? Just consider this. Alright, so we are talking about, let's say, suppose that this is the Earth, and this is a question for you. Let's say this is the Earth, and we have 2 points. Let's say this is one point A, which is located in the low Earth orbit, and we have another point B, which is in the high Earth orbit. Let's say this is low Earth orbit, and this is the high Earth orbit. One at, let's say, almost 500 kilometers from the surface of the Earth, and another one at 35,076 kilometers from the surface of the Earth. Now, in this way, if I ask you, which is a better place, A or B, which is a better place for taking images and videos of the Earth? Which is a better place to take the images of the Earth? Alright, whether A or B. I'm launching the poll, giving you just 10 seconds. Please mark it quickly. To take the images of the Earth, whether you would want to be at A or whether you would want to be at B. So 59% of you are saying A and 41% of you have said B. So can you also give me the reason why you think A or why you think B? Okay, Chaitanya, your explanation is correct. Saloni correct. RP correct. Raghav correct. Achal correct. Alright. So most of you. Okay, so for A, I understand what people have written, and I also see why people have marked B. The correct answer will be A. And let me tell you why. A very simple logic. Suppose that you have a camera. Let's say you have a phone camera, right? Now, this phone camera, if you have a phone camera, whether you want to keep your camera near to the object where you're taking the pictures from, or would you want to keep it away from the picture just to clear, just to have a wider range? Largely, you want to take high definition pictures, you want to take clearer pictures, and if you want to take clearer pictures, you always want to be near the object or the subject of which you're taking the image. So you're not really concerned about whether you are taking the picture of everything. Largely, you're concerned about the subject, whether you can take a very clear high definition HD picture of that subject or not. And this is the same logic that applies to the satellite images as well. That if you are at A, then you'll be able to take better pictures, you'll be able to take clearer pictures, high definition pictures, and it will be more useful for you. Whereas when you are at B, of course, you'll be able to take a wider range, but that wider range will not be helpful because the pictures will be of poorer quality. Now, just imagine this, that we have a satellite which has been placed for disaster management. Right? So if you have a disaster management satellite, you would want very high definition pictures and videos of an area. Suppose that the pictures of a flooded area is being sent by the satellite. So then if this picture has been taken from the low Earth orbit, then you would have a very high definition picture, and you'll be able to understand what's happening on the ground, and you can plan your mitigation strategies accordingly. But let's say you had taken the picture from B, then of course you would take a wider picture, but that's not the concern. Right? So that's why A. That's why our preference would be A if images of the Earth is concerned. Similarly, let's say if it is about communication satellites. If it is about communication satellites. So in case of communication satellites, whether A or B, which is the preference? In case of communication satellites, whether A is the preference or B is the preference. And please also tell me the reason why you feel A or why you feel B. Wonderful. So 76% of you feel that it should be B, and 24% of you feel that it is A. The answer here is B. And yes, as many of you have written, that B covers wider range. In communication, more important for you is the range. More important for you is how much area can you cover while communicating, so that you can provide a better communication. Can we keep a communication satellite at A? The answer is yes, we can. But the problem will be that, let's say, look at this picture. Look at the picture that you have in front of you. Suppose that you have a communication satellite in the low Earth orbit versus a communication satellite that you have in the high Earth orbit. Suppose that you have a communication satellite here and you have a communication satellite here. Now, if this satellite is covering this much area, then parallel to this satellite will be able to cover this much area, right? It will be able to cover this much area, right? So this satellite is only covering this much area, whereas this satellite is covering this much area, right? So that is what we will see. So that's why covering from A is also possible. I'm not saying that we can't cover it from A, right? I'm not saying that we can't cover it from A. We can cover it from A, but the area that is being covered by B will be better. The area being covered by B will be better as compared to the area being covered by A. So now what happens is that if you are keeping a communication satellite at A, then you'll have to keep multiple such satellites. You'll have to keep multiple such satellites so that all these satellites together, they can provide the kind of communication that you need. So what work would have been done by just one satellite, perhaps will be done by 10 different satellites when you are at A. So that's why it's not that it's practically impossible to keep a satellite at A for communication. We can, we do. And for example, if you know about the Starlink project, if you've heard about the Starlink project, do you know about the Starlink? Have you heard about the Starlink? You have? Great. So yes, SpaceX, correct. So this is a project by SpaceX to provide space-based internet, and they are keeping their space-based internet for the satellite communication satellites at A. Now, because of that, they have multiple satellites. They have to use multiple satellites. So instead of multiple satellites being used, if let's say you keep it at B, there are other technical reasons why they are keeping it at lower orbit. It's not that they did not know this, and I know this, and the entire SpaceX did not know about this. Of course, they knew, but there are other technical reasons because of which they have to keep it at A. But what happens is that when you keep a satellite at B, what you can do with one satellite, you perhaps will have to do with the same work with 10 to 15 satellites. So obviously, it is not cost effective in that scenario. So that is why communication satellites largely will be kept at B, and the satellites which are kept for images and videos and Earth observation largely will be kept at A. So that's why height becomes a very, very important factor. The second factor is eccentricity. Now, what does eccentricity determine? The shape of the orbit. This is what we discussed, that the value of E is between 0 and 1, and when it is 0, it is circle. When it is approaching 1, it is very highly elongated ellipse. So because of that, whatever the shape that we need. For example, many of the communication satellites, we need a circular orbit. Many other satellites, we do not need that circular orbit, we need an elliptical orbit. So depending on what kind of application we have, depending on why we have launched the satellite, depending on that, the eccentricity is first calculated and accordingly the satellites are launched. And then the third important factor is inclination. Now, when it comes to inclination, we are talking about inclination from the equator. So either the satellite could be at the equator, having let's say 0 degree inclination, or maybe 1 to 5 degrees inclination, or they can be inclined. So on the basis of inclination, we can have an equatorial orbit, there can be equatorial orbit, or there could be polar orbits. And we'll discuss more about these orbits coming just in a second. So this is basically how we determine these factors, and these three are the most important factors that determine any kind of orbit. That determine, and these are the factors that we'll have to fix depending on our requirement. Depending on our requirement, we fix all these factors, and hence it helps us in devising any plan for any given satellite. Now, one by one, we'll have a discussion on all these different types of orbits. Also understand that what we are discussing here, all right, why I'm also giving some of the context of what we have just discussed in the last, let's say, half an hour or so. It's also because if you understand these areas well, if you can even carry the facts of what we are discussing here, a lot of questions which are seemingly current affairs questions, they can be solved even without knowing current affairs. Even without knowing the details of the current affairs, a lot of questions can be answered. And we'll also take some examples where you'll see that. But this is what can happen. It's just about linking all that information together. That how do we launch a satellite? What is the basic principle of launching the satellite? The three laws of planetary motion, the factors that determine the orbit, the different types of orbits that now we are discussing based on all the information that we have just collated. So what happens is that if you can relate all this information together, a lot of times it makes it much easier for you to answer a question in the prelims examination. Because in prelims, sometimes the questions we have seen that they go beyond an expected limit and they can actually be a little more difficult. So maybe they are not. I mean, most of these things are not even directly required for your mains examination, but in the prelims examination, they are very often going to help you. So first we have the low Earth orbit. Now, what are the points that we know about the low Earth orbit? First and foremost, we know that the height is between 180 kilometers to up to 2000 kilometers. Correct? The height is 180 to 2000 kilometers. What kind of satellites are used here? We launch Earth observation satellites. Earth observation satellites. So anything that will observe the Earth. Earth observation satellites, the ones that are also called as remote sensing satellites. Why remote sensing? Because they are remotely sensing or remotely observing the Earth. So hence they are also called as remote sensing satellites. So Earth observation satellites are also called as remote sensing satellites. Height is 180 to 2000 kilometers. These are Earth observation satellites. Then one more thing, just remember this, the launch vehicle, and we'll discuss about this. The launcher that we use, the launch vehicle that we use is a PSLV. What is a PSLV? We'll discuss later, but just remember for now that we are using PSLVs here. Also, one more important point, that their orbit period is 1.5 to 2 hours, meaning that they complete one revolution around the Earth in 2 hours. So they're very quick because they are very near the Earth, so that's why they take very less time as compared to high Earth orbit, where we discussed that it takes 24 hours to complete one revolution. Here it hardly takes 1.5 to 2 hours to complete one revolution. So that's also a very, very important point. Then apart from that, generally speaking, what we see is that these are lightweight satellites. These are lightweight satellites, normally up to 1500 kg. Normally they have a total weight of up to 1500 kg. So that's why these are lightweight satellites. And then lastly, their total life cycle. The total life cycle is of, generally they are 2 to maximum of 5 years. 2 to maximum of 5 years. So they do not, they are not operational for very long. They are not operational for very long also for a reason that these are very near the Earth. Being near the Earth also means that there is a very strong gravitational force that they are being pulled with. So that's why they also carry extra amount of fuel so that they can be kept in the required orbit. And that's why the wear and tear in these satellites are also very high. And that's why they do not remain operational for very long. As compared to that, when it comes to the high Earth orbit, the satellites there very easily, they are operational for like 15 years of time, or sometimes even 20 years of time. So that's why life cycle is less. Life cycle here, we see that it's just 2 to 5 years. And this is mainly because they have they feel a strong gravity of the Earth. Strong gravity of the Earth, that becomes a reason why this is where why they are not functional for very long. Now, when it comes to the low Earth orbit, we see that there are two types of orbits that we have here. One called as the polar orbit, and the second one called as a sun synchronous orbit. Now, this sun synchronous orbit also, we say that it is a special case of polar orbits. We say that these are special case of polar orbits. Now, why special case and why the name sun synchronous? All right, why are we calling this as sun synchronous orbit? So the name sun synchronous has been given because they are synchronized with the movement of the sun. What does it mean? Simple. Let's say a satellite which has been kept at sun synchronous orbit, it will be synchronized with the movement of the sun, meaning that suppose that it is overhead Delhi at 10 a.m. in the morning, then every day in the morning at 10 a.m. it will be overhead Delhi. It will be synchronized in a manner that it will always be overhead Delhi exactly at 10 a.m. So that's why sun synchronous, because it has been synchronized with the movement of sun. So basically this is an orbit which is, we say that it is synchronized with the local solar time. It is synchronized with the local solar time. So local solar time, basically when we say, it means that if let's say it is overhead Delhi at 10 a.m., it will be always overhead Delhi at 10 a.m. in the morning. Now, there could be a question that might arise here. On one hand, I'm telling you that the orbit period is of just 1.5 to 2 hours. And on the other hand, I'm also saying that 24 hours later, 10 a.m. in the morning, it will be overhead Delhi. Why so? Can you tell me this? Can you think of this? That even though it is completing one revolution just in 1.5 hours, why does it come back overhead 24 hours later? Yes, Janvi, you are correct. Pratham correct. Deepika correct. Saloni correct. Ilma correct, Swati correct. So you get the point. So what we basically see is here, if you look at this diagram, what happens is that by the time this satellite completes one revolution, the Earth would have also moved because of the rotation of the Earth. So it starts from this point, but it does not, after rotation, after completing one revolution, it does not come back to the same point because the Earth has rotated. The Earth has rotated. So it comes down to the same latitude, but it does not come back to the same longitude, right? It comes back to the same latitude and does not come back to the same longitude. So similarly, the next time, so first time it was here, after it completed one revolution, it has come back here. After the second revolution, it will come back here and so on. So that's why it is synchronized in a manner that 24 hours later, it should come back to the same point where it started from. Now the question is, why to do this? Why are we so concerned about keeping it fixed? Why do we want it to come back to the same point at the same time 24 hours later? The reason here is that this will help us in having consistency in data. That, for example, let's say you have an Earth observation satellite for climate change studies. So for climate change studies, you need to understand the conditions day after day, given all the other conditions remain the same. So then in that case, when you are at 10 a.m., you know that the conditions at 10 a.m. will be more or less the same. Suppose that it was not synchronized. If it was not synchronized, what happens then? Once it comes at 2 a.m., maybe then 6 a.m., maybe then 10 a.m., maybe then 2 p.m. and 5 p.m. and so on. So then you do not have consistency in data. When you have synchronized this will give you consistency in data. Right? This will help us having consistency. So the data that we are getting, it will be consistent because you are taking the observation at the same time every day. And that's why sun synchronous orbit is used. Many times you'll see that in the newspapers, it will be mentioned as SSPO. So SSPO because sun synchronous polar orbit. Sun synchronous polar orbit. Because we are seeing that it's a special case of polar orbit. So that's why when you look at a news that a PSLV C54 has been sent or PSLV C52 has been sent, you'll see that they'll mention that it has been launched to SSPO. In the newspaper, it will be written SSPO. So SSPO is sun synchronous polar orbit. So hence, we see that this is basically what it is. So that's why just remember all this information together. Now, how it helps you. Just understand how it helps you. There was a question on AstroSat. I think 2016 paper, there was a question on AstroSat because AstroSat was launched in 2015. So they asked a current affairs question from AstroSat. Now, to launch AstroSat, we had used PSLV. One of the statements given about AstroSat was that it is a 2000 kg satellite. Can this statement be correct? The answer is no. Why? Because we used PSLV and we are using lightweight satellites. Lightweight satellites are launched using PSLV, as you can see here. So when you combine these two pieces of information, you know that it cannot be a 2000 kg satellite. So now, let's say if you don't know that these two pieces of information are related to one another, what happens is that you will go there and you say that why have they asked such a factual question? So if you know the concepts, these are not factual questions because you know that beyond 1500 kilometers, beyond 1500 kg, it's not possible for us to launch a satellite with PSLV. Another example, if I give you. The IRNSS satellites, we are going to discuss about IRNSS later, but IRNSS satellites, the first 7-8 satellites that we launched it with the help of PSLV. All of them were launched with PSLV. Why? Because they were all satellites which had lesser weight, maximum up to 1400 kg, nothing beyond that. The latest satellite that we have launched, if you know about this, the latest satellite that we have launched, I think in the month of May, I think it was 30th of May exactly, or 29th of May when it was launched. This was launched with the help of a GSLV. Why GSLV? Because it's a 2200 kg satellite. It's a 2200 kg satellite. So because it's a 2200 kg satellite, we cannot launch it with the help of PSLV. But all the previous IRNSS satellites, they were launched with the help of PSLV because they were all lightweight satellites. So all these pieces of information, they help you. And if they have to confuse you in information, this is how they can do it. They can just try to mix up the information. So that's why all these points that we are noting here, they can be very, very important points. So how exactly do we use these satellites? These are the various aspects of the usage of the low Earth orbit. And this is a list that I've taken from ISRO website. This is a direct list that I've taken from ISRO website. ISRO has listed out that these are the various applications in Earth observation or remote sensing for which ISRO launches a satellite to the low Earth orbit. All right? These are the various applications for which low Earth orbit satellites are launched or polar satellites are launched. Understood? So now, for all these, you need to remain close to the Earth, and hence we see that all these are the applications of Earth observation. Now, when you look at the examples of Earth observation satellites, we have Cartosat, OceanSat, ResourceSat, ReSat, MineralSat. There are all these. So, basic nomenclature, if you understand, the basic nomenclature here, the naming of the satellite is basically the application plus sat. This is a basic way in which we name our satellites. For example, the satellites which are supposed to be for cartography, meaning mapping basically. So, cartography satellite has been called as Cartosat. For ocean resource, OceanSat. For resource monitoring, ResourceSat, and so on. So, this is how the nomenclature in general has been about the Indian Earth observation satellites. Correct? Understood? So this is about the low Earth orbit. Then after this, we have the medium Earth orbit. Now, in case of medium Earth orbit, what we know is that this lies between 2000 kilometers to up to 35,786 kilometers. Correct? This is where it lies. Now, here we have two types of orbits. One called as semi-synchronous orbit and second one called as Molniya orbit. Now, semi-synchronous orbit is called so because it completes 2 revolutions in one day. This completes 2 revolutions in a day. 2 revolutions in a day. That's why it is called as semi-synchronous. So that's why in 12 hours it completes 1 revolution. Now, the height at which this is located is 20,200 kilometers from the surface of the Earth. 20,200 kilometers, and this is the orbit that is used by GPS. The GPS satellites that we use, for example, for Google Maps, etc., when you are looking at the navigation, GPS is the satellite that largely is used. So GPS uses this semi-synchronous orbit. Right? So semi-synchronous orbit is a kind of medium Earth orbit because it lies between 2,000 to 35,786 kilometers. Now, second orbit is a very interesting orbit, the Molniya orbit. And the picture that you see here, the picture is of the Molniya orbit. Now, this Molniya orbit, just understand this, as you can see, that it is a highly eccentric orbit, right? It is a very highly elongated ellipse, correct? Now, this Molniya orbit is an orbit that was designed by, or we also said invented by, designed by Russia. It was designed by Russia for its communication needs. Now, the question is why? So, generally speaking, when it comes to communication satellites are equatorial. Generally, you'll see that the communication satellites will be kept here in the equatorial orbit. Then why did Russia have to invent an orbit? Why Molniya orbit was required? Because when you look at in general, let's say if this is the range of a given satellite, all right, given satellite in an equatorial orbit. So it is able to cover, let's say, an area like this. It is able to cover this kind of an area. Russia, what happens here is that the polar areas of the North Pole and the South Pole can't be covered well. Now, a large land mass of Russia is in the North Pole or near the North Pole. So that's why an equatorial orbit, an equatorial communication satellite is not as useful for Russia as it would be for other countries. So that's why Russia thought that this kind of an orbit is not really useful for us. We need another orbit that it can be useful for us, and hence they basically they had designed this orbit. So and they said that this is something that will help us. Now also see how Kepler's second law is applicable here. Right? Kepler's second law is applicable here. What was second law? That when you are nearer the central object, you are faster. When you are away from the central object, you are slower. So look at this now. Earth lies almost at one end of this ellipse. So when the satellite is in the southern hemisphere, it will very quickly move away from the southern hemisphere, and it will remain in the northern hemisphere for a very long time. Right? So that's why it will be very, very helpful for Russia. And why would they care about what happens in Antarctica or even Australia for that matter? They are designing this orbit for their own needs. So hence they have created this highly eccentric orbit so that this orbit can remain in the northern hemisphere for a very, very long time. So that's why second law directly is applicable. So I'm just writing it here. Kepler's second law is applicable in Molniya orbit. Now, there's a very interesting story about this Molniya orbit. That yes, this is the side of Russia. This was USSR back then. So this is the side of USSR that we needed this, and hence we have designed this. US did not share this opinion. US said that this orbit has been designed by the USSR so that they can keep their spy satellites in this orbit, because this is a new orbit. Nobody knows about this orbit. Nobody can see anything that is there in this orbit. So that's why USSR will use it so that they can spy on US and they can spy on other European countries. And that's why they have made this orbit. It's not for any communication needs. This is just a whitewash that USSR is doing. And of course, this was the time of Cold War. Anything that US would say, USSR would not believe it. Anything that USSR says, US would not believe it. So that's why US said that no, this is not going to be a communication satellite orbit. This is an orbit. This is going to be used for spy satellites. This is what they believe. Now, whether that was true or not, whether USSR actually did it or not, nobody knows. Nobody will ever know. So, but this is what the official. We need to believe the official stories more than the other urban legends that we have around this kind of an orbit. So this is basically what happened, and this is the Molniya orbit. Now, when it comes to the medium Earth orbit, most importantly, it is used by GPS. Now, when it comes to GPS we know is called as the Global Positioning System. Now, this Global Positioning System is something that is owned by the Air Force, the US Air Force, and it is a satellite system, a set of 32 to 34 satellites. The numbers keep on changing. That maximum number is 34. Right? Maximum number is 34. Sometimes it is 32. Sometimes even it is lesser than that. So these are satellites which are at 20,200 kilometers, and they basically provide the navigation information, positioning information to the entire Earth. Now, GPS is being used. I mean, for example, if you have used Google Maps or any kind of maps like that, you'll see that they actually are mostly dependent on GPS, because in India also the services of GPS are available. Now, when it comes to GPS system, there is one concept that becomes very, very important, and not only for GPS system, any navigation system, and something which is called as triangulation. So triangulation is when, to determine a single location, there are a set of 3 different satellites being used. That you provide the location information of a given area, not with the help of just one satellite, but rather with the help of 3 different satellites. Why so? So that you can increase the accuracy. So that the accuracy of this determination of location can be high. Because, for example, let's say if this kind of an area is being covered by this satellite, this kind of an area is being covered by this satellite, and this kind of an area is being covered by this satellite. So when all these 3 are providing the information together, they'll be able to provide a much higher accuracy as compared to if there was just one satellite. So that's why this method of triangulation is used. So triangulation basically is when you have a set of 3 satellites providing the location of an area. Okay? So that's why we see that this is how we see that triangulation as a method is used by GPS and is used by other navigation systems as well. So, and not only 3, I mean, in case of GPS, they also keep a 4th satellite to provide an extra accuracy, extra precision to the data that they are providing, to the data that they are giving you. Now, in case of IRNSS, let me come back to this question later. All right, I'll come back to this question later. So this is basically something that we need to understand about the low Earth orbit, and this was the medium Earth orbit. Now coming to the high Earth orbit. Now in case of high Earth orbit, again you can see that there are 2 types of orbits here. One is geosynchronous orbit called as GSO, and one is geostationary orbit also called as GEO. And in this case also, you can say that this is a special case of GSO. Why we are calling it as a special case, we'll discuss that as well. Now to talk about the various aspects of this orbit, first of all, the height here is 35,786 kilometers, as we have discussed. Then application largely various different types of communication. So you are launching communication satellites here. Then the launcher that we are using here, the launcher here is GSLV. So PSLVs cannot be used here. GSLV is used. And again, we'll discuss about PSLV and GSLV later. So don't worry for now. Then these are heavy satellites. Largely you'll see that they are more than 2,000 kg. They can be very, very heavy. I mean, some of the satellites that India has launched, they are more than 6,000 kg. They're so bulky. So they are heavy satellites launched by GSLVs. Then after that, we had discussed about the orbit period. So orbit period here is of 24 hours. It completes one revolution in 24 hours. And lastly, the life cycle. The life cycle of these satellites, they will be 15 to 20 years. They can be 15 to 20 years. So that's why they will actually be much greater. I mean, the life cycle will be much higher as compared to the lower orbits. So because you are away from the Earth, so keeping and maintaining the satellites at this particular point is easier. So that is also one of the reasons why communication satellites we don't launch in the lower orbit, because first of all, you need a lot more satellites, and secondly, you have to keep changing those satellites. That's not the problem that we have with the higher orbit. So that's why from that perspective, higher orbit is much better for us as compared to the lower orbit for communication. Now, when we are talking about these 2 orbits, one being the geosynchronous orbit and the second one being the geostationary orbit. Understand the differences between them, and more than differences, why are we calling them as, why we say that geostationary orbit is a special case of geosynchronous orbit. So just talking about the factors. So we had discussed that there are three basic factors, right? Three factors. What were the factors? The first factor was height. First factor was height. So on the basis of height, both are fine. Both are 35,786 kilometers. So this is the first factor. The second factor that we had determined, so this is the first factor. The second factor that we had talked about was eccentricity, or in a manner you can say the shape. Eccentricity basically determines the shape. Now geosynchronous orbit is elliptical in shape. Whereas geostationary orbit is circular in shape. It is circular in shape. Now, what is the difference that this makes? Ellipse can be, when you have an elliptical shape, there can be a lot of different types of ellipses, right? It can be a highly elliptical orbit, it can be kind of a circular elliptical orbit, and so on. But whereas when it comes to the circular orbit will be a perfect circle, right? Perfect circle, where the radius even has been already determined, because the height is fixed. So in a manner, you can say the radius is fixed and it is circular. Okay. Then you have the third one was inclination. Right? The third factor that we had talked about was inclination. Now, inclination, what we see is that geosynchronous orbit, they can have a small inclination. Small inclination, meaning that 2 degrees, 5 degrees, 7 degrees, they can have inclination. And in case of geostationary orbit, they have 0 degree inclination. All right. So now just understand this. That for geostationary orbit, height is fixed, meaning in a manner you can say that the radius is fixed. Then it is circular, so the shape is also fixed. Then inclination is also fixed. So because all these factors are fixed, what happens is that in this case of a geostationary orbit, it is a unique orbit. There is only one such orbit. Only one orbit. All right. Whereas when it comes to geosynchronous orbits, here multiple orbits are possible. So understand the difference here, because all these factors are fixed. That's why geostationary is one single orbit, whereas there are multiple different types of geosynchronous orbits which are possible. So that's why if you see this is what we understand, that this is basically the line of your equator, correct? This is the line of the equator. So geostationary orbits, they lie on the plane of the equator, 0 degree inclination, whereas geosynchronous orbits, they can have an inclination from the equator. So that's the basic difference between them. That's why we are saying that geostationary orbits are special case. They are a special case of geosynchronous orbit. So that is basically what we understand here, the difference between the two. Now, in case of these orbits, we see that the satellite, they will largely be used for satellite communication, all the different types of communication, whether one-way communication or two-way communication, they can be used in all the different ways. So that's what we see with satellite communication. So whether it is telephone, telemedicine, teleeducation, mobile communication, radio communication, television, in all these cases, we can make the use of these satellites. And when it comes to these satellites, in India, there have been two families of satellites. We have INSAT series satellites and GSAT series satellites. Now, INSAT and GSAT, they are not different. The difference between INSAT and GSAT has been on the basis of the launch vehicle that has been used. Initially, we did not have the capacity to launch our own communication satellites, because these are very bulky satellites, and we did not have the capacity to launch bulky satellites. At that moment, largely it was INSAT. Right? Then after that, we built our own launch vehicle, the GSLVs, and after we started using the GSLVs, they became GSAT satellites. So that's a basic difference in the nomenclature between INSAT and GSAT. Otherwise, they are not different in their functionality. Functionality is the same, launcher is different. All right? Same function, different launcher. So that's the difference. Otherwise, there is no difference between these two satellites. Now, coming to the navigation that we are looking at from Indian perspective, there are two types of navigation satellites that we are using. One called as Gagan, second one called as Navik. Now, between Gagan and Navik, these are the two types of navigation systems that India has been using. Now, remember that when it comes to our navigation systems, largely other navigation systems are in the medium Earth orbit. Whereas when it comes to our navigation system, it's a mix of medium Earth orbit and high Earth orbit. It's a mix. So one by one, let's try to understand what is the Gagan system and what is the Navik system. So first we have the Gagan system. Now, when it comes to Gagan system, it stands for, so if you see this, Gagan stands for GPS aided geo augmented navigation. GPS aided geo augmented navigation. That's a GAGAN, Gagan. Now, this is something that was a joint project of ISRO and Airports Authority of India. These two came together and they basically had made this Gagan system. And this is something that was largely meant for civil aviation, to help civil aviation in India. Civil aviation, how to help? In general, let's say, suppose that there is a flight that has to take from one place to another. Suppose that you have a flight that has to take from Kolkata and it has to come, let's say, it has to come to Bangalore. Then in that case, what happens is that it is never a straight line path. If you think that it's a straight line path, it can't be. Anyway, also because of the rotation and other factors, it can't be a straight line. But what we see is that it takes a very large distance. That the distance that it takes for overall to come to the final destination, it takes a lot of time. So the total path length is more, meaning that it is covering more distance. More distance means more time. More time also means more fuel consumption. Correct? More fuel consumption, more time, also costlier. So we wanted to reduce all this. We want that it should take as less distance as possible. The time will be lesser, then the fuel will be saved, money will be saved, environmentally it will also become friendly. So there are all these factors, and also to provide a safety to the civil aviation. This is something that was determined. Now, apart from that, there are other things also it can help in. So it's not only that it helps in civil aviation. There are all these other activities also where the Gagan system can be helpful. So if you see a typical Gagan architecture looks like this, that there will be geostationary satellites. There are 3 GSAT satellites that we have launched, which are being used here. We have GSAT 8, we have GSAT 10, and we have GSAT 15. These are the ones that are being used for the Gagan system. So as you see that these geostationary satellites are used. Apart from that, the GPS satellites are also being used. So both of them, they are being used together, and by being used together, they will provide the required information for civil aviation in the country. So that's why these are required for the emerging demands of the civil aviation requirements to meet the user requirements of positioning, navigation, and timing. So now understand this, that when it comes to Gagan, this is what the Gagan system has been. Apart from that, we have the IRNSS system. Now, IRNSS stands for Indian Regional Navigation Satellite System. So, Indian Regional Navigation Satellite System, or IRNSS. Now, this is a set of 7 satellites. Initially, a set of 7 satellites where you have 3 geostationary satellites and 4 geosynchronous satellites. So, as you see, you have this geostationary 1, geostationary 2, and geostationary 3, and you have 4 geosynchronous satellites, GSO1, GSO2, GSO3, and you have GSO4. So 4 geosynchronous satellites and 3 geostationary satellites. And overall, they cover the Indian subcontinent and up to 1500 kilometers beyond the Indian borders, largely to cover the Indian Ocean region. All right, to cover the Indian Ocean region, this is how the IRNSS system has been devised. Now, when it comes to this IRNSS system, what we know is that it will provide positioning, navigation, and the timing services for users over India as well as region, extending up to 1500 kilometers beyond the Indian boundaries. Now, in this particular system, we know that it's a set of 7 satellites, 4 geosynchronous, and 3 geostationary. Now, why this combination? Also understand that this combination also helps us in carrying out the triangulation, something like this. So what we discussed, that a set of 3 satellites are always used. So this is how the set of 3 satellites can be used in providing the triangulation for the NAVIC system. So now that's why 3 geostationary on the equator and 4 geosynchronous having slight inclination from the equator. So now this is how basically this is being provided. Now when it comes to this IRNSS, there are 2 types of services that IRNSS provides. One called as the standard positioning service, and the other one is also called as restricted service, or this restricted service is also called as precision positioning. Another name for it is precision positioning. Now, overall, just understand this, that when it comes to the requirement of IRNSS has been very, very important satellite system for us. And why exactly has it been important? Because we somewhere in our history we understood that we need to have our own navigation satellite, and we cannot forever be dependent on something like a GPS. And largely the context, you can say the context was set in 1998 and 1999. In 1998, you might know that India did a nuclear test. And this nuclear test is something that India had to keep under the wraps, because no country wants that somebody does a nuclear test, a nuclear weapon test also, that is. So that's why India did not announce it, and it is something which was being done. It was being kept as a hidden project, although the US Central Intelligence Agency, or the CIA, they had some information about this kind of a project being carried by India. So that's why with the help of GPS satellites, they were constantly monitoring BARC, Bhabha Atomic Research Center. They were constantly monitoring Indian subcontinent with the help of their satellites. So in a manner, they were spying over us, right? In a manner, they were spying over us. And this is 1998. Somehow we were able to fool that system, and we were able to do the test. Otherwise, if they had known before the test had happened, they would have put all the pressure possible on India, so that India does not do the test. But thankfully, we were able to do the test, and we knew that these kind of activities were happening. This was 1998. Then in 1999, during Kargil War, we know that Pakistan had reached the line of control from the side of Pakistan occupied Kashmir. They had come to Kargil, and this was the moment where they had an advantage of altitude compared to the Indian side. So that's why for us it became very, very difficult. And this is where we also again we went to US and we asked for the navigation and the positioning information of that area, so that India can plan accordingly. US refused. Knowing what was happening, US refused. And this was a big moment for us, a big realization for us, that why we can't be dependent on countries like US, especially for navigation related information or these kind of security related issues. So 1998 and 1999, you can say that these were 2 years of learning for us, that why we need our own navigation system. Then after that, you see that 2 years later, 2001, our discussion starts. 2003, we start working on the IRNSS system. By 2013, we are ready. 2013 onwards, we start launching these satellites. So between 2013 to 2018, we launch all these satellites, a set of 7 satellites for the requirement of navigation over India. So, and the positioning that we get is supposed to be better than 20 meters, meaning the accuracy is of 20 meters, can be much lesser than that. The recent data that we have fetched from IRNSS satellites, we see that now this has been brought down to even lesser than 10 meters, meaning that if they have pointed one area, it is in the 10-meter radius of that area, which is very, very high accuracy. GPS also gives accuracy of up to 5 meters, which is even better, but even we are heading there, and very soon we'll also be at that position. So recently what we have seen is that apart from these 7 satellites, there is this satellite NVS-01 that also has been launched, and this is what I was telling you about, that this is a 2232 kg satellite, and this has been launched with the help of GSLV. And this is just May 29th, this year only. This is something that has been launched. So now one thing which is also very, very important with respect to NVS-1 is that it has indigenous atomic clocks. Atomic clock basically is highly precise clock. It's a highly precise watch, you can say, that provides you information about timing to a very, very small precision, to a very, very high accuracy. So that's why, and this time, remarkably, this is something where we have used our own atomic clocks. We have designed our own atomic clock. So this is, you can say, in a manner, the 8th satellite, an addition to the existing 7 satellites of IRNSS to provide a better information. And going forward, you can say this is the phase 2 of navigation, where we are now improving upon the navigation requirements. So this is basically what we see. Look at this question. This question was asked in your paper. Read the question, and then I'll launch the poll for you. All right, let me launch the poll. Please mark your answers. So 50% of you have marked A, 25% B, 18% C, and 8% D. I needed more correct answers than this. It's a very, very easy question. Satellites used for telecommunication relay are kept in the geostationary orbit. They are kept in the geostationary orbit. A satellite is said to be in such an orbit when the orbit is geosynchronous. This is correct. We had discussed that geostationary orbits are special case of geosynchronous orbits. Second statement is orbit is circular. This also we discussed that it is a circular orbit. The orbit lies in the plane of the equator. This also we discussed that it has a 0-degree inclination. Right? We discussed this. The orbit is at an altitude of 22,236 kilometers. What is the height? 35,786 kilometers. I've been repeating this term so many times. I mean, at least 10 to 15 times I would have said 35,786 kilometers. How would you mark this as correct? And look at this. You have 4 here, 4 here, and 4 here. The correct answer had to be A, even without knowing the first three statements. The fourth statement was the easiest statement, and you could have determined the answer from there. So that I expected more correct answers. I don't know what happened here, but I expected more correct answers here. One more question on IRNSS. Please read the question. Again, it's a very easy question. Okay, so I'm launching the poll for you. Please mark your answers. So 57% of you have marked A, 30% B, 7% C, and 6% D. With reference to Indian Regional Navigation Satellite System or IRNSS, consider the following statements. First is IRNSS has 3 satellites in geostationary. This is correct. We discussed this. And 4 satellites in geosynchronous. Right? So this is fine. IRNSS covers entire India and about 5,500 square kilometers beyond its borders. This is wrong. How much is it? 1,500 kilometers beyond Indian borders. So that's why this is wrong. India will have its own satellite navigation system with full global coverage by the middle of 2019. It's an Indian regional navigation satellite system. We are not doing the full global coverage. India and 1,500 kilometers beyond Indian borders. So full global coverage is not even a factor. And middle of 2019, it's already gone 4 years back, and we did not really have anything like that. So 3 is wrong. So C especially cannot be your answer. The answer is A. That is 1 only. 2 and 3 are wrong because 2 is factually wrong and 3 is anyway wrong. I mean, 3 is a very you can say extreme statement to say, and anyway, it's not related to what we are actually trying to do. Okay. Now, coming to some of the other satellites that we have. So we also have some satellites which are meant for space science. For example, we have AstroSat, Mangalyaan, Chandrayaan 3 being the latest example. So these are the ones which are not related to any application that India has or Indian society has. It is more of experiment based on space research. So that's also, these are also some of these satellites. Then apart from that, there are certain satellites which are called as experimental satellites. And these experimental satellites are the ones which are used for some kind of experiments, right? These are used for some kind of experiments. So let's say we have to test out a component, we have to test a new sensor, we want to do something, or let's say a new launch is supposed to happen in coming couple of years. So we want to test out certain components of it, defense related applications. So in all these cases, there are certain experimental satellites also which are launched many times. So INS-1A, INS-1B, etc. are used here. Then after that, we also have small satellites. Right now, in case of small satellites, what we see is that small satellites are satellites which are less than 500 kg. The satellites which are less than 500 kg, they are called as small satellites. Now, in this small satellite range also, there are various different types of satellites. There is something called as mini satellite. Then we have micro satellites. Then we have nano satellites. And then after that, we have pico satellites. So these are the 4 types of satellites which are called as small satellites, where first we have mini satellites. Now, mini satellites have mass between 100 to 500 kg, right? 100 to 500 kg. Micro satellites largely between 25 kg to up to 100 kg. Nano satellites, which generally are between 1 to 25 kg. And pico satellites are less than 1 kg. So this is how we determine this different types of satellites. Now, what happens in this particular case is that when it comes to all these satellites, especially when it comes to nano satellites, what we see is that nano satellites out of all these different types of satellites have been crucially important for us. And over the past 10 years especially, you'll see that nano satellites have gained a lot of market, not only in India, but also all across the world. So understand why, all right? Understand why something like this has happened, that nano satellites, they basically have taken over the world. They have created a market of their own, and a market to which we'll see that the entire world has been responding, including India. That in India also, we see that a lot of these satellites are being used. So understand this. And even from means perspective, I would say that this is a very, very important point. That the question could be, let's say, why nano satellite market is growing, why nano satellites are gaining market, or it could be about simply they can ask you just what are the advantages of nano satellites. So there are a lot of ways in which they can ask you a question about this. So just think of an answer. Okay? I have the points. I also want you to contribute here. Can you think of the points that why nano satellites have become so important? Why over the past 10 years we have seen so much of nano satellites being in the news? Okay, cost effective. Many of you have written. This is correct. They are cost effective because these are small satellites, so it does not take a lot of effort. So yes, they are cost effective. Correct. Purpose specific. Crucial point. All right. So I'm writing this down as well. Purpose specific. Then yes, less expensive. So we have written that it is cost effective. Yes, easy to launch is also correct. That it's easier to launch. So I write this here instead. Takes less time and effort. It takes less time and effort to launch these satellites. So that's why they can be developed rapidly. They can be constructed very quickly and at a low cost. So yes, less time in manufacturing as you've written, so that's correct. Easy to launch also is fine, so that also we have written. Cheap production, so that is what less time and effort, and that's why we are trying that. This is also there. What else? Marketing support, yes, you can say that, and we'll discuss about that point as well. Experimental satellites, so that's correct, but not really as an advantage. Okay, still let me write this. So experimental satellites. What else? Yes, influence students to take part in research. Very good point. So we see that a lot of student satellites are also being launched now, which are largely nano satellites or sometimes also pico satellites. So student satellites are also being launched. This is also a good point. Multiple satellites can be launched together. This is also correct, that we can launch multiple satellites. So for example, in India, in 2017, we made a world record. Right? In 2017, we made a world record where we launched a total of 104 satellites in one single launch. In one single launch, we launched 104 satellites, which became a world record. It became a world record because no other nation has been able to do that. India became the first such country to do it. And out of these 104 satellites, 103 satellites were nano satellites. 103 nano satellites and only one bulky satellite. That was what we did. And we created a world record. Before this, the record was with Russia with just 38 satellites, and we launched 104 satellites in one single go. So this is also correct. So now, apart from that, what we see is that a lot of experimental satellites, when we say a lot of technology testing can be done very easily now. So technology testing can be done very easily with the help of these satellites. So that also becomes very, very important part. Then apart from that, what we see is that the deployment can also be very versatile. That we see that network constellations or constellation of satellites can be also made, which we say that multiple satellites can be launched simultaneously. So in a manner, you can say that it makes it the deployment versatile. So versatile deployment. Right. Then apart from that, we see that a lot of connectivity can be provided, and more importantly for India, apart from all these points that you have mentioned, you have mentioned a lot of points. So, but I'm just summarizing all this and just looking for one point that you have missed here. Yeah, Naveen, you are on that track, what I was talking about. So this becomes a very, very important source of revenue generation. It becomes a very, very important source of revenue generation. So when, for example, when I'm saying that 104 satellites were launched in one single go, out of those 104 satellites, 103 satellites were nano satellites, and a total of, out of 104 satellites, there were only 3 Indian satellites. One Cartosat series satellite and 2 INS satellites. There were only 3 satellites that were Indian, and 101 satellites were foreign satellites, out of which 95 were from US and others were from other countries. So these 101 satellites that we launched, it also, of course, generated a lot of revenue for us, and this is something that we are now also moving towards, that we see that this is helping India in building a space market infrastructure development in India. It is leading to this. Apart from that, what we also see is that it is also helping in a lot of employment generation, a lot of job creation or employment generation. We see that a lot of startups are also coming up in these areas. So it is also helping us in building a lot of this kind of a culture, and thus it also brings in a lot of investments. It also brings in a lot of investments for India, and that is the reason why, through with the help of NSIL and with the help of InSpace, we'll discuss about these later. All right, we see that these have now come into the picture. Now we have something called as SSLV, or Small Satellite Launch Vehicle, which is specifically meant for these kind of satellites. We'll discuss about this also later. But overall, the thing is that until now we were dependent on PSLVs or GSLVs for any kind of launch. Now what we see is that SSLV also is coming into the picture, so that we can launch these small satellites. So that's also something that we are working on. And lastly, we have university or academic institute satellites. These are the satellites which are made by students or with the help of the faculty and the college. And this is where the launch is done by ISRO for free. ISRO does not charge anything for these kind of launches, and in a manner it also supports the students. It also supports the engineers or the scientists who are in this particular area, because ultimately, if these satellites are being launched, it will also generate a lot of curiosity and interest in the minds of the students, and we'll see that a better development of space infrastructure or space market can happen in India, and better understanding of how to launch satellites, etc., will happen, which will lead to a better infrastructure altogether, better growth in this particular segment from the perspective of the students as well. So that's why in all these cases we see that India has been growing, and that is also helping in one way or the other. Let's look at this question, and this is where we'll end the session for today. Just read the question. There's one mistake here. This had to be 3 only and 1, 2, and 3. This is typing mistake. Please read the question and mark your answer. Okay, so 50% of you have marked D, 20% C, 23% B, and 6% A. For the measurement or estimation of which of the following are satellite images or remote sensing data used? This is the question. First is chlorophyll content in the vegetation of a specific location. Can we determine the chlorophyll content? The answer is yes, we can. See, chlorophyll, you might know that it is a pigment which is green in color. So, if with the help of Earth observation satellites, our remote sensing satellites, we try to calculate or we try to identify the intensity of green color. All right, we analyze the intensity of green color. So, this analysis of intensity of green color. So that will determine the amount of chlorophyll that we have in the vegetation of a given area, and that will also help us in understanding whether they are getting enough nutrition or not. Is there an extra irrigation support required or not? So in agriculture, this will have a major use. So this is correct. Second is greenhouse gas emission from rice paddies of a specific location. Correct. This also is possible because greenhouse gas emission also means that there are certain wavelengths or there are certain waves also that will be emitted here, infrared rays, for example. So we determine the intensity of that, and that will give us an idea of whether greenhouse gases are emitted. And which kind of greenhouse gas? Rice paddies. When we are talking about which greenhouse gas? Methane. Perfect. Right. So this greenhouse gas is methane. So we are trying to identify whether methane is being emitted or not, and we can actually find that by analyzing the images that we are getting. Then the land surface temperature. Now land surface temperature is again related to the infrared rays, because wherever you have heat, you have infrared waves. So these infrared rays, whatever are being emitted, they can be determined, their images can be taken, and we can actually find this as well. So this is correct. Now this question actually had come in the context of a satellite called as HISIS, hyperspectral imaging satellite. All right, this was hyperspectral imaging satellite. So when we say hyperspectral imaging satellite, hyperspectral imaging means that you are trying to take images in each and every part, each and every small part of the electromagnetic spectrum. That's why hyperspectral imaging. So that's why we can take images of infrared, radio waves, microwaves, visible light, green color, red color, all these things. So that is why HISIS can actually give us information about all these different things, and that is the context in which this question was also asked. Right. So let's end our session here. We'll start with Lagrange points when we come back tomorrow. If you have any doubts, if you want to ask anything from whatever we have discussed, please let me know. US GPS is much clearer than India's GPS-5. Nothing as such yet. I mean, accuracy-wise, yes, they have better accuracy. They have had atomic clocks which have been better, but now we also have improved upon it, and we have been closing the gap that we have there. Which launch vehicle used in launching of 104 satellites together? It was PSLV C-37. PSLV C-37. Difference between INSAT and GSAT. See, INSAT and GSAT, the difference has been on the launch vehicle. GSAT is after we built our GSLVs, after we started using GSLVs, we named the satellites as GSAT, and before that it was called as INSAT. Today's Indian Express has 4 or 5 SNT articles. Wow, I'll have to check. Option 2 is not clear. Why rice paddies? So not rice paddies, the greenhouse emission, because we also want to understand the impact on climate change from these kind of rice paddies. So that's why those kind of determinations can also be done from there. Please repeat geosynchronous and geostationary in high Earth orbit. So let me go back to the slide where we discussed this. Yeah. So what we are saying is that in case of geostationary orbit, I'm saying that geostationary orbit is a special case of geosynchronous orbit. So if you see this, geostationary orbits, they lie on the plane of the equator. They are on the plane of the equator, 0 degree inclination from the equator. Whereas geosynchronous orbit can have a little inclination, can have a 5 degree inclination or 10 degree inclination like this. Also, geostationary orbits are circular. They are circular in shape. They are a perfect circle. Whereas geosynchronous orbits are elliptical. So that's why because of these kind of changes, we are saying that geostationary Earth orbit is a special case of geosynchronous orbit, and that's why the term geostationary. Why geostationary? Because it is stationary. I'm just writing it out here. It is stationary with respect to a point on the Earth. That's why the term geostationary is being used here. How comet held by metallic material? So they have metallic material. I mean, this is how the composition is. This is what we have observed on any comet. So this is what we have seen. Leaderboard, I'll show the leaderboard, but today's leaderboard does not really show the exact leadership. Perhaps the people who are rank 2 are the actual rank 1s today, because there was one wrong answer that I had marked. Where these satellites go after being dysfunctional, they do not go anywhere. Many times they remain in that same orbit, and they become a part of space debris. We'll discuss what are space debris in the next class. Why there is high amount of carbon dioxide on Venus? So it's about the formation itself. While the formation of the planets were happening, we see that these kind of compositions, they automatically had built on these planets. So that's why it's not something that has happened. And these are things that also evolve. This also changes over time. So it's not that it remains fixed always. There was a time that when Earth also had a lot of greenhouse gases and carbon dioxide, but now that's not the case. CMB, please explain. So cosmic microwave background you are saying. So what I'm saying is that at the early time of the universe, during the birth of the universe, we say that the temperature of the universe was very high, 10 to the power of 32 degrees Celsius. And then after that, expansion started. So now when we look back, I mean, when we are looking through the telescope and when we see the early part of the universe, we see microwaves there. So microwaves basically are the parts of the electromagnetic spectrum which actually are associated with heat. All right, they are associated with heat, and because they are associated with heat, that's the reason why this heat remains from the early universe is actually visible as a background, as a cosmic microwave background. For how much time Chandrayaan 3 would work? I think for the next 2 weeks it is going to work. How falling meteor led to an extinction? So mainly what happened there was that the impact would have created a lot of, I mean, it would have just created impact, and dust clouds, etc. would have been created, blocking the sun for a very long time, and hence photosynthesis, etc. could not happen, and every individual flora and fauna that was dependent on sunlight, they died. So that's why almost 85% of the flora and fauna was extinct. Just like the geostationary orbit is unique orbit as only a single orbit possible, can we say that same about polar orbit in the low Earth orbit? Not really, because it depends whether it's a circular orbit or not. What is the exact inclination at which we are keeping it? So we shouldn't say that. After the formation of the universe, why only Earth has been having vegetation and many flora and fauna? Why not other planets? Because we, first of all, we lie in that Goldilocks zone. We are at that perfect position with moderate climate. So that has been a major factor. And if this exists for any other planet anywhere else in the universe, they might also have been sustaining life, just that we don't know about it. There could be a very different kind of life that they are showing. Can we visit Halley and Ladakh? Yes, of course you can. Right. So I think I have covered most of the questions that you had. If meteor and asteroids are both found to be beyond Pluto, then how do you differentiate between them? It's a very fine line. Largely, when we say asteroid, we think of asteroid as a broken part of a planet, but not the same for comets. So that's a basic way in which we can determine, or even for the meteor, for that example, meteorite also for that matter. We don't see them as a broken part of any celestial body, but for asteroids, we see them as a broken part. Right. So this is it. Let's end the class here. Please go back, revise everything that we did today. There are some complex parts that we discussed. So please go back and revise everything. If you have any doubts, please bring them back tomorrow. We shall discuss the same. So this is the end of the session for today. Thank you very much for joining.